Learn to build a complete large language model from scratch using only pure PyTorch. This course takes you through the entire lifecycle, from foundational concepts to advanced alignment techniques. You'll begin by implementing the core transformer architecture and training a tiny language model. From there, you will modernize and scale the model with production-ready enhancements like ROPE, mixture of experts layers, and mixed precision training. The course then transitions to the full alignment phase, where you'll implement supervised fine-tuning and build a reward model. To complete the lifecycle, you'll use proximal policy optimization, or PPO, to align the model with reinforcement learning from human feedback. By the end, you'll have the deep hands-on experience needed to build and customize your own LLMs.
Hello everyone, and welcome to LLM from Scratch, a hands-on curriculum in PyTorch. This is going to be a long, practical journey where we build modern large language model components entirely from scratch, one step at a time. I'll be speaking at a fairly slow pace, so if you're comfortable, I'd actually recommend watching this video at 1.5 times or 2x the speed, adjust to whatever feels natural to you. So why this course? Now, there are many tutorials that show you how to use large language models. There are many who show you how they are built too. So the likes of Umar Jamil, Sebastian Rachka have all been a source of inspiration to me to learn how LLMs work. And they've built some superb material around this, and I highly recommend you check them out as well. The objective of this course, however, is to show you the end-to-end workings of modern LLMs in one place through code. We will use the minimal necessary force when it comes to theory. And this course will start from the absolute foundations, how transformers work, how the attention is computed, how to train a tiny toy model on your laptop. And then, step by step, we'll add all the modern tricks: rotary embeddings, RMS norm, mixture of experts, supervised fine-tuning, reward modeling, and finally, reinforcement learning through human feedback. By the end, you won't just know how to run a model, you'll understand the building blocks of what makes models like GPT work, and you'll have implemented them yourself if you follow along. Now, let's talk about setup. The requirements are actually pretty modest. We need a laptop with Python, PyTorch, and optionally CUDA if you have a GPU. But a GPU is not mandatory to follow along. You can do everything that we do here on your CPU itself. They just run slower. Here's how the course is structured. So we'll start with part 1, the core transformer architecture. We'll implement the core transformer architecture from scratch. The attention heads, the multi-headed attention, the feed-forward layers, the positional embeddings, the layer norm, and stacking everything into one block. Part 2, we'll actually train a tiny LLM. We'll do this on a small text file, but we'll do all the bells and whistles around the tokenization, the batching, we'll understand the cross-entropy loss, the sampling, and the evaluation part of it. Part 3 will modernize the vanilla transformer architecture. Will include RMS normalization, rope, swig-glue, KV cache, sliding window attention, and more. Part 4 will scale it up. So we'll go from byte level to BPE byte pair encoding tokenization. We'll add gradient accumulation. We'll explore how to do mixed precision training. We'll do checkpointing, logging. All right, so part 5 will be mixture of experts. We'll do some theory over here. We'll explore the routing, the gating, the stability tricks, and hybrid dense plus MOE blocks. Part 6 will cover supervised fine-tuning. So we'll dive into instruction datasets, formatting prompts and responses, and evaluating outputs. Part 7 will implement a reward model using pairwise preference datasets, and we'll explore a few loss functions like Bradley, Teddy, and margin ranking loss. And then finally, in part 8, we'll bring it all together with RLHF using PPO, proximal policy optimization, adding a value head to our policy, scoring completions with our reward model, and optimizing a KL penalized objective. This is the same basic recipe that powered the first versions of ChatGPT. This course is designed to be hands-on as possible. Every part comes with a modular, well-commented code that you can run, tweak, and extend. So if you see here, we've got all the parts figured out. I'll link the GitHub in the description. So every part consists of each module that we're going to pick up here. It's all organized into orchestrator.py. That's your entry point. So if I look at part 1, I'll try to find this orchestrator.py. Part 2, same thing goes. So the orchestrator.py will be the starting point of every module, and then you can work your way inside from there. Again, as we'll explore each and every module, things will become clearer. That's the roadmap. I hope you're excited to dive in. Grab your laptop, set up the environment, and let's start building from scratch. Welcome to part 1 of LLMs from scratch. In this video, we'll talk about the overall architecture or the workflow that we'll follow, along with hyper focus on just the transformer part, the vanilla transformers as we know it. So if you look at this GPT assistant training pipeline, and it's split into 4 major stages, and we'll cover all of them in our series today. There's this pre-training, that's step 1. Now, this is where you spend the most amount of money. This is where a sizable chunk of the internet gets processed to tens of trillions of tokens. And then they bring out what is called a base model, which then is used for further processing. This is the step where thousands of GPU and months of training and all of the big models come into the picture. The supervised fine-tuning stage is the second stage from there. Relatively sparse data requirements and compute requirements. And this is where we go from the base model behaving like a purely next token predictor to more like an assistant. From there, the alignment stage starts, where you don't want the LLM to present biased political views or something along the lines of abuse and quality and security. So you come up with a reward modeling step, and then finally the reinforcement learning from human feedback. In this video, we're only going to focus on the vanilla transformer, as the paper in the year 2017, Attention is All You Need, came out with. So we have on the one hand the transformer architecture. This consists of the encoder and the decoder. We'll only focus on decoder only because LLMs are mostly decoder only transformer architectures. So the input is first tokenized, and then it goes through an embedding step, and then the embeddings go through a positional encoding step, and then from there it's split into 3 parts to Q, K, and V. And the zoomed in version of this box, masked multi-head attention, is over here. So the 3 splits that we had for the embeddings, they go through their own linear layers, and then a scale dot product attention, concatenate the output of all of the heads, all of the different heads, and then finally through a linear layer. Now this is the zoomed in version of the scale dot product attention, where the QKV goes through a matrix multiplication and then a scale component. And then we will use the mask and the filling component because we are focused on the decoder only architecture. So if you were to implement an encoder only architecture, you won't be focusing on this. And then finally put it through a softmax and then matrix multiply it with the V, and outcomes. So whatever comes out of here is actually this, and then it's all concatenated. So the different heads spit out different outputs that are all concatenated, sent through a linear layer. And then finally, whatever comes out of the multi-headed attention is then added, or a skip connection is present with the previous input, and then normalized. So we go through layer normalization in this case, then through a feed forward, and out with the softmax and the logits and probabilities. Again, I wanted to keep this a very theory light course, so we'll only go through the bare essentials of what is required so that we can proceed towards implementation. Now, this entire block is called the layer of a transformer, and you can stack up however many layers as your desire to implement a bigger and bigger network. So the more layers you apply, the bigger your model gets. So we'll jump right into the code with that perspective, And then hopefully once you see how the attention mechanism and all of the neural network is configured, it'll provide you a better perspective. So we are only going to focus on part 1, and this is the repository layout for part 1. As always, for each part, the entry point will be orchestrator.py, which runs the different demos and the tests, and you can go double click deeper from the orchestrator.py. Treat that as your starting point. So we have the different modules here. So we got the POS encoding. There's a small attention NumPy demo for perspective, what a single head of attention looks like, a multi-head, a feed-forward network, what the entire block looks like, the attention mask, and some visualization utils to help you visualize things along the way. So what we first do is we add in this argument for visualize, and it will write out some matplotlib visualizations on our out folder. So if it doesn't exist, we make them, and then first things first, we run the dummy attention demo, but we'll skip that for now. We'll try and understand the actual attention mechanism that we just studied. So it all starts with demo mha shapes.py. So we'll open that up, and first off we import the multi-headed attention, and then we set the hyperparameters for our model. So B is going to be the batch size, T is going to be the sequence length of a particular row of data. You can assume this as the context length. The D model is going to be the embedding dimension, and then we also define the number of heads that are going to be configured in our scale.product attention mechanism. Now, the core idea is the D model gets split into the number of heads that you configure here. So if your D model has a dimensionality of 12 and your N head is 3, then each head, it'll first be split into 3 heads, and then each head will be of size 4. So it is essential that they be divisible by each other. Otherwise, an error should be thrown. All right. So we make some dummy inputs. So X equals torch of random distribution, random normal distribution of the batch size, the token sequence, and the D model. And then we pass it through a multi-headed self-attention. So in order to invoke a block for the multi-headed self-attention, we take a D model and the number of heads. That's all that is required. We log things along the way, and once we run this, we'll be able to visualize all of the output. Now, what I've done here is written all of the log output in a file so that it can be studied later. So once our attention block is defined, we pluck out the QKV component of it, and then we run it through our input. So imagine this to be the output of the embeddings of text. So whenever text goes into a large language model, first it's first tokenized, and then from there each token is converted to an embedding dimension. We will study these two things in great details later down the parts, but we are not going to build tokenizers and an embedding layer in this particular part. So we push it through the QKV part, and then we get our QKV back. Now we'll actually have to split it to get our individual QKVs. So we'll have to configure them right along batch size, token size, and then 3 of N head cross D head. So if you have N number of heads, it will be split along the number of heads that you have and the D head that you have and the combination of the D model. So once you unbind your QKV, you actually can unpack your individual Q and K and V. The Q and K will get transposed, ready to be matrix multiplied, and then we compute the scale. So again, if you focus on the equation over here, then the Q gets multiplied by the transpose of K, and then it is scaled by D of K. Now the DF model is actually the global dimensionality of the embeddings, and DK is the dimensionality of each attention head that you use. So in our case, our embeddings are configured to be of 12 embedding dimension, and then we have 3 heads. So D of K in our case will be 4. So we configure the scale parameter like so. So it's the inverse of the square root of each dimension of a particular head. And then we finally compute this part. So the QK transpose and then divided by the scale parameter. So we're focusing on the expression over here. So if you see, we are matrix multiplying Q with the transpose of K and then multiplying it by the scale. Now, since I've already taken the inverse as our scale, I need to multiply it and not divide it. So I've computed the part where Q and K transpose are computed along with the scale. So I'll take the softmax of these scores and then directly multiply it with the values matrix, which will give me the output. So once I get this output, this is the output of the attention mechanism. I just have to push it through a feed forward network, and then finally I get my output, right? Now, we skipped a bunch of steps here. We haven't gone inside what a multi-headed self-attention is and what are all of the different components like the attention mechanism, the QKV, and the project. We'll do that right now. So this file, multihead.py, represents one multi-headed attention module. So this is again importing from the NN module. And the important thing to understand here is the flow or the dimensionalities that change along the way. You'll get an input of batch size, sequence of tokens, and a D model as input. Now, once you push it through the QKV, you're going to make 3 copies of X of the above matrix. So what you will end up with is a batch size token, but 3 times D of model. So you'll get 3 copies of the QKV. And then you push it through the 3 linear layers, and then you get your 3 individual Q, K, and V, where each is N cross head times D cross head for each token and batch, right? So there'll be 4-dimensional tensors over here, and they will be split along this dimension, the QKV. Then we'll have to transpose them and then compute the Q times K transpose and then scale it by the square root. We've already seen this before. What you'll be left with is again a batch of N head cross T tensors. And then finally, we'll have to softmax. We'll have to apply softmax on top of it and then multiply it with the weights matrix, which will give us a batch of N head cross D of head. Again, if you follow the simple rules of matrix multiplication, you'll be able to get this very quickly. And then finally, the merge step happens where we concatenate all of the different heads together. So this will simply be along the 3rd dimension, the number of heads that were there and the dimensionality of each head, which will bring us back to the D of model. So this is the output of every multi-headed self-attention mechanism. If we go through this, we initialize our module through an assertion statement first, and if this itself is not satisfied, it will raise an exception saying the D model must be divisible by the N head. It's a nice guardrail to have. There's an N head which is passed by the user when they are invoking. So in our case, we passed the N head as 3. Then there's a D head, and D head will simply be the D model divided by the number of heads, the quotient part of it. That's why you see the double slashes. Then there's a QKV. So each Q and K and V will have their own set of linear weights. So what this takes as input is a D model, and it has weights outputting 3 times D model, right? So we're going to do this matrix multiplication in one shot. So we don't have 3 linear layers for each of Q, K, and V, but we have 1 linear layer that represent all of Q, K, and V, and then we'll split it in retrospect. And that's why post the QKV happens, there's a view and a split method that we're going through after this, right? From there, the projection layer is just a linear layer, Optionally, you can keep a dropout. So it's configured to 0 by default, so we won't have dropout unless you configure it explicitly. And then trace shapes true literally gives you some good bookkeeping facilities of plotting and printing all of the shapes so that you can track them along the way. Now, this is what a forward pass looks like for a multi-headed self-attention mechanism. So we have the BTC split into the X dot shape, and then from there it goes through the QKV. We rewire the QKV to unbind it to give us our individual Q and K and V. Then we apply transpose to all three of them, and then finally we configure our scale matrix multiply Q and K, and then put it through a causal mask. Now this is the important part where we had mentioned that there's a masking step. So Q and K gets multiplied and then gets multiplied by the scale, and then there's a mask step that is optional, which is nothing but the upper triangular matrix. So this essentially is a Boolean value that will return true if you configure it so, and then that true will change the matrix you apply it on and set it as 0. So let me try and explain this a little more. So what we want to essentially do is, if we have a matrix like so, and this has, let's say, various elements in it, and I want to apply a masked fill, that essentially means the upper half of this diagonal should be set to 0. So this part. So what we are essentially implementing is we invoke an upper triangular matrix that simply says true in these cases. So it's basically a matrix that is filled with booleans, where the elements that we want to essentially remove are set as true. And then when we do in PyTorch what is called a masked fill, then we will pass this matrix over here, configure it with this, the masked fill. We'll see this in a minute. And then what will happen is, whenever this is true, that particular element is set to 0. So if this is true, this will set to 0. If this is false, the element will stay as is and the values won't change. So in our case, we will substitute it with -infinity, because softmax of -infinity simply gives you 0, which again then implicitly turns off all of our parameters to 0. The reason why we do this is in large language models, you essentially don't want to see the tokens that are further away or in the future of the current token that you're processing. So if you have a sentence, the cat sat on the mat, then if you're focusing on this token and trying to go through your decoder only architecture to get an output, you don't want to look at these tokens, right? So if I'm processing these tokens, all I can look at is the previous tokens, including itself. So if I'm processing this token, I can look at everything here and previously till my context window. So by the time I get to mat, I'm probably only looking at this window, right? So if there are words beyond the word mat, I cannot and should not be able to look at them. So that's the core idea of the mask fill. So if we come back to our code, the causal mask function simply returns a Boolean of the desired dimensionality, where it fills up with ones, and this will be treated as a Boolean for whether to apply a masked fill. So we'll watch that in a minute. So I take my causal mask over here, and then I do the attention matrix that I got from previously, and then I do a masked fill with the mask as the input. So I'm informing where all I want to replace this matrix with -infinity. So where all this mask matrix will be true, the attention matrix, the positions in the attention matrix will be replaced by -infinity. And then when we take the softmax of the attention matrix, the -infinity will go to 0. And that's how we call it turning the attention off, or turning these tokens off. And then finally, there's a dropout. Again, in our case, it's not applicable. And then we matrix multiply the weights by the values matrix. Again, if traces is true, we print the shape, we'll watch it, and then we'll reconfigure it to put it through the projection layer. So here we are transposing the dimensionalities 1 and 2, and then making it contiguous. So fun fact, transpose actually breaks memory allocation in PyTorch, and that might be a problem when you're trying to do further processing down the line. So it's actually essential for us to apply this contiguous part, right? All right. So torch.tensor.contiguous is easy to understand. It returns a contiguous in-memory tensor containing the same data that you pass in. If it is already in the specified memory format, it returns the tensor itself. So it will be the same data, but the memory allocation will be contiguous. Now, why do we need this? So the view here will just return the same data, but with the reconfigured dimensionality that you specified. And for view to work, you actually need the matrix to be contiguous. Now, if you want to avoid using two operations one after the other, you can also use reshape, which returns a copy of the data. This is a nice thing to do. It saves us some memory, but I don't think it matters eventually, because contiguous again reallocates the data in memory, and then view just rewires it with the same data. I think you can achieve the same thing through reshape. And then finally, we return the output, which brings us back to our multi-headed self-attention, and everything else follows like we just discussed. So in the multi-headed attention, we went through the causal mask, and that I think was the only piece that was missing for us to understand this properly, right? Couple of things that we have skipped is the positional encoding. So let's go through that. So the idea is whenever you send text through large language models, again, they get tokenized and there's an embedding, but they also incorporated with positional embeddings. And this will give it a sense of it matters a word appears in what position. So what we have implemented here is an absolute positional encoding, which essentially means that if you again have a sentence, the cat sat on the mat, then this position will be given a certain positional embedding, and that will get added to the original embeddings of this word itself. So if the cat has a certain embedding, it will be added to the positional encoding that we have come up with for the even position or the second position. So there'll be one for the third, one for the fourth, and so on. So each position will have an absolute positional embedding, and it doesn't matter whatever word comes, its embedding will be added to that corresponding positional embedding. So how do we calculate the positional embedding? Well, there are two ways to do it. We'll go through the sinusoidal positional encoding, because that's the one implemented on the 2017 paper. I've got one more that you can go through. Again, we'll eventually evolve this to doing rotary positional embeddings, so might not matter. So for the forward, we take what you give me. So this will be B cross T cross D model, and then I'm just adding my positional embedding that I have for those particular dimensions. So I come up with torch zeros. So this is for the context length, and this is for the embedding dimension. And then I arrange them. So this A range goes through 0, max len, and then unsqueeze, meaning it adds one more dimension to this particular vector. And then this calculation, again, it's mentioned on the paper. So I have the original paper open in front of me, and here's what the positional encoding suggests. So we've given a couple of formulas. Again, there's a formula for odd positions and there's a formula for even positions. So depending on the word was seen on the second, fourth, sixth, or the first, third, or fifth, the positional embedding will be slightly different. So here we come up with a division term, and then depending on whether it is the odd position or the even position, we apply sine or cos. Then position times the division term, exactly as it mentions on the paper. And then we register this as a buffer. This is another interesting PyTorch property, which essentially says that this will be used in the forward propagation, but we don't need to store the gradients. So these are not learnable parameters. They are calculated once and they are absolute. So we again take the words, tokenize them, create embeddings, and then from there we add our sinusoidal positional embedding to get the inputs for the attention mechanism. Finally, in order to visualize the attention mechanism better, I've also implemented this in NumPy. So let's say the output of the embedding is our X, will be batch size 1 and a sequence of 3 tokens, or sequence of 3 and a D model of 4. So each token will have 4 dimensions here. So those are the 3 tokens that are coming in as input. I have the linear layers WQ, WK, and WV. So I'll multiply them with the individual ones. Now remember that in our PyTorch implementation, we did this in one shot and then split the QKV. We're doing the opposite here, just so you have more visibility into this. And then we finally print the different shapes. We calculate the scale by hand. And this is just, I think, a more simplified and a better view that you can run over and over again in NumPy in order to visualize the attention mechanism better. So feel free to tinker around once you get a hand on this. And then finally, we machine learning engineers, a subset of software engineers, further hate writing tests, but I think they help a lot. So I've written a couple of tests here, and there will be some tests that wherever I feel I struggled with it personally, I have included unit tests so that you can try them on your own as well, just to make sure that the math is correct on this one, right? So the X goes as input and I come up with random QKV. Now what I'm trying to test for is the shape of it, right? So if I set a seed, I get a tensor X. So I create a torch tensor out of my NumPy array. There's a single head self-attention mechanism that I've implemented here. So this is what it does. So it's basically a subset of the multi-headed self-attention where we don't do the multiple heads. It's just one single head. It's just a simplified view of the multi-headed attention, right? So if I come back, so we take a single headed attention block, and then the Q in the single head self-attention will be filled by these weights. So the WQ over here will be copied over to the weights of the Q that we have configured here. Again, if I open the single head, one of the components is the Q part. So the weights of this linear model will be copied over to the Q part in this attention mechanism. So the same goes for K and V. And then finally we run it through the attention mechanism to get the output and the weights. And then we assert that the shape is going to be 1, 3, 2. Again, based on our inputs, this should be the right answer. And then hopefully everything works out. So what we'll do now is also go through some visualization utilities that are written. I won't be going through them in detail. but this will help us visualize attention better. So without further ado, we'll actually run the code and then see the output for ourselves. So I'll go Python orchestrator demo, and then I will pass it through the visualize parameter. So again, if I come back to the orchestrator, all of the instructions on how to run and what to pass are given over here. So I'm already inside my part 1 folder. This is where you need to run it. And then once you run it, it runs the attention NumPy demo that we've already seen. So it goes through each and every matrix, giving you complete white box visibility into each shape so that you can visualize it yourself. And then finally, we run our demo multi-headed attention shapes.py. So the input over here goes as 1, 5, 12. So where 1 is the batch size, 5 is the token sequence, the number of tokens, and 12 is the embedding dimension of each token. Now, if you push that through QKV, what you'll get is 3 times what was there before. So 1, 5, 36, that checks out. Now, if I have to split it into QKV, I need to view it in 5 dimensions. So I take this and I split it into 1, which is the batch size. 5 again is the token sequence. 3 is literally hard-coded to Q and K and V. The second 3 is the number of heads, and 4 is the dimensionality of each head. And then from there, each Q, K, and V will be 1, 5, 3, 4 respectively. Again, if I transpose only dimensions 1 and 2, so these 5 and 3 get swapped to 3 and 5. So we'll get 1, 3, 5, 4. And then from there, if we multiply Q and the transpose of K, then we'll get 1, 3, 5, 5. Again, Q with the transpose of K. So this dimension, along this dimension, if we multiply, then we'll get 1, 3, 5, 5. And then finally, we apply the softmax. That does not change the dimensionality. Then we'll multiply it with the V, and V is again 1, 3, 5, 4. We multiply that with again 1, 3, 5, 5. If we do that, we'll be left with 1, 3, 5, 4. Then we merge each of the heads. So with each head, we'll get 3 separate 1 by 3 by 5 by 4 matrices, and then if we concatenate them along the dimensions, then we'll get 1, 5, 12, and the final projection will be 1, 5, 12. And then we included a small legend for each of the acronyms and what they stand for. And then there's an entire visualization module as well. So if I come back to VS Code, you will see that there's an out folder which also logs everything to a file so that you can view it. It's more organized that way. And then for each head, we had 3 heads, remember. For each head, the key and the query have been put together as a scatter plot. Now, since again, we are using a decoder only LLM, you'll see that the upper triangular part has been turned off. So for each token, so we had 5 tokens going in, so 0 to 4, you'll be able to visualize the strengths of the weights between the key and the query, and that will again give you more perspective on what you're doing, right? So that brings us to the end of the first part. So we started with the decoder only attention mechanism. We have not covered tokenization and creating embeddings. Should be fairly simple, but we've parked it aside for later down the parts. We went through the most vanilla positional encoding. We opened up the masked multi-headed attention to understand the QKV and the concatenation, all of that. And then we opened up the scale dot product attention mechanism as well. Went through a bunch of math, and hopefully now you have good perspective on how to implement your own attention mechanism with PyTorch. Hello and welcome. Welcome to part 2 of the LLM from Scratch series. In this part, we are going to try and train a tiny LLM with byte level tokenization, dataset batching and shifting for next token prediction, cross entropy loss. We'll do the training loop from scratch. No APIs required. We'll look at some of the generation parameters like temperature, top K, top P sampling, then evaluation based on a validation dataset. So as always, our part 2 also starts off with the orchestrator.py, where the entire layout is laid out like so. We'll go through some of these aspects and then go very deep inside the train.py. We'll be spending most of our time. So the orchestrator.py runs 3 scripts. The training.py, the first parameter for which is a data set. Now you can take any text file that is lying around on your laptop. I've chosen Hindi. There's a bunch of poems over here, but I've also included in the repository some English text that you can use in order to train your model. So once the data is locked in, we're going to pass on these hyperparameters. So we're going to be training for 400 steps. We're going to sample after every 100 steps so we can evaluate for quality. We're going to evaluate after every 100 steps. Our batch size is going to be 32 and our block size is going to be 128. Block size is essentially the context window of the operation. We're going to have 2 layers or 2 blocks, 2 transformer blocks in our model. We're going to go for multi-headed attention where the n head is 2 and the embedding size will be 128. So without further ado, let's start from the train.py. So I've got an exhaustive list of parameters here, some of which we've passed to from the orchestrator.py. So the data, the out directory I've hard-coded to be the runs folder where we'll save our model weights. The block size we passed is 128, batch size 32, n layer 2, n head 2, n embedding, which is our embedding size, is 128. We've chosen not to use dropout, but you can. The steps, the learning rate, the weight decay, again, we're going to be using the Adam optimizer. We'll also use gradient clipping to stabilize our training so that one particular batch of data that was really off from the rest of the training data does not throw our model off course. With eval interval, we're going to set it to 100. That's what we passed from the orchestrator.py. Eval iterations, sample every, that means every 100 steps or so. We'll take the latest checkpoint and then sample a bunch of tokens just to see the quality, how many tokens we want to sample, the temperature, top P, top K, these are the generation parameters. If this is passed, no matter whether you have a GPU or not, this will only train in CPU. Whether we want to compile our model or not, and then AMP stands for automatic mixed precision training. So we'll explore all of that as we go along. So first things first, if you have a GPU lying around, it'll be automatically picked up. So we're saying it's CUDA if torch.cuda is available and args.cpu. So this has to be false. And you have to have a GPU available, then you default to CUDA, otherwise it falls back to CPU. So the first things first, we're going to make a tokenizer, the byte tokenizer, and then we're going to make our data set, which is this text file, based on our tokenizer, and then we have a GPT model. So let's go very deep into these 3 aspects first, and then we can come back and continue the flow. So first things first, the byte tokenizer. So this is the implementation of the most basic tokenizer that is there. It literally takes every character and treats that as a token, and it will return the byte information of that position in the UTF-8 space. And then what will happen is you'll have a very finite vocab length, but you will have a lot of tokens to process. So this is not exactly the kind of tokenizer you would want to use in an industrial strength setting, but it's a very good tokenizer to get started with. And further down the parts, we will explore an industry grade byte pair encoding tokenizer. We'll go through the training and the merging steps as well. So this has an encode step where I'm literally returning the UTF-8 encoding of that particular string, which is a list of characters, and then decoding is the exact opposite, right? So I'm returning the character of a stream of bytes if passed to me, and then it has a property that we can use called the vocab size. So that's our tokenizer. Now next, I'll need to take my text file and create a data set out of that based on this tokenizer. So here I've got dataset.py. So here, literally what I'm doing is taking the path of the text file that will be passed, and then we'll read the bytes information off of it. So in this case, we don't need to use our tokenizer, because reading the bytes itself ensures that the text file is getting encoded in UTF-8. So the data variable will just be a stream of bytes that are already tokenized, given that we are using a byte tokenizer. We convert that to a Torch tensor, and then in order to train test split, we're going to take a 90-10 split. So 90% of our data will go on training, the rest of it in validation, and then the block size is nothing but the context window. Now, in order to sample a batch from this, what we're going to do is you're going to send a parameter called which, choose to. So this will either be train or validation, and then the batch size along with the device. So I'm taking a buffer here, says self.train if which equals train, else self.val. And then I'm putting in a small assertion here that the length of this buffer should at least be more than the context window that you've chosen. So essentially, when you get your hands on this piece of code, the way you want to run it is you want to choose a data set whose 10% is more than the context window that you've set. So 10% of this text file should be more than your context window, and that will ensure that this condition will be satisfied. Now, if it isn't the case, you can just take the subset of the block size. That's fine. So from here, we're trying to get a random batch, and there's a trick that we're using over here. So we'll take a random integer from 0 to the length of the stream minus the block size. And then from there, that integer is seeded from the start to a block size for the number of indices that you sample over here, which is essentially this batch size. So this will return 32 integers, and each integer will be between the starting point, which is 0, and then however many characters you have in your text file minus the block size. Let me try and explain this further. So let's say you have 1000 tokens at your disposal in your text file, and you've set the block size as 128. Now, each of these 1000 tokens or characters will have their own token ID. So there'll be a list of tokens, a list of 1000 tokens. So there can be 0, 1, and so on, right? Now, I want to make sure when I sample an integer, I sample an integer from 1000 minus 128 minus 1. Now, what this will return is an integer between 0 to this. So what I can do is now, let's say this is ix. Now I can take this random integer and then take it all the way from this integer to the block size that I've set. What this ensures is it does not overflow. So if, let's say, you sample the 999th character here, I don't want to add the block size and then spill over this list. So I'm keeping a buffer somewhere here so that even if it samples the last integer from here, I still have a lot of leeway to go till my batch size. So I select 32 such integers, and then from there, I take them from the index to the index plus the block size for each element in my batch. Then I stack them up, and then what I want to do is for every token X, its corresponding Y will be the next token. So the starting point for my Y will be I plus 1, and then I plus 1 plus self.block size. So that sort of plus 1 is taken care of here by the minus 1. So again, we're just trying to ensure we don't spill over. So we put it onto that device and return that as a batch. So we're back to train.py. Hopefully we've understood what the tokenizer is and the byte dataset is. Now, another thing to keep in mind is that you would not be keen to use this again at scale, because we're literally loading all of the data in memory. So what you will have as an example will be partition Parquet files, probably, if you're dealing with data at scale. So you want to load it partition by partition as a batch and not read the entire data set in memory. Again, we'll just get an out of memory exception for the terabytes and trillions of tokens you'll be trying to process. So then finally, we get to our model invocation, and for that, we're passing the vocab size, which in this case we're taking from the tokenizer. And if you remember, we had set that to 256. So our vocab size will be 256. The block size, we've set it to 128. We're only going to do 2 layers, 2 heads, 128 embedding length, and then dropout will be default, which is 0. So we're not using any dropout, and then transfer that over to the device. Again, CUDA or CPU. So let's dig deep inside the GPT model that we've got. Now, the heart and soul of this GPT model is, of course, going to be the attention mechanism that we've already studied in the previous part. So we'll just have a very summarized explanation for the causal self-attention part, but then we'll also try and put that together to look to see how the entire model looks like. So for example, we did not cover layer normalization as part of our previous part. We were only focused on the attention mechanism. So some of the properties that we need to set for this class are coming in from the parameters of the initialization itself. So we'll set the block size. We'll set the token embedding, where the input to this embedding module is the vocab size and the output is the embedding length. So in this case, 256 by 128. The same goes for the positional embedding. And then from there, dropout optional. Then we have a list of modules, which is nothing but blocks. So in this case, our n layer is 2. So we'll come up with a module list of 2 blocks over here. And then the PyTorch layer normalization is something that we've chosen to use, not implemented from scratch. And then finally, the head, which is the linear layer, goes from an embedding to the vocab size. And this is what will eventually get decoded. This will be the logits. Then the logits will go through a softmax and then diffused across probabilities. So we also apply the initial weights. So if we see that a module is an instance of a linear layer, then we initialize that with a mean of 0 and a standard deviation of 0.02. So as per a normal distribution. If the bias is not none, I think we have not chosen any bias for this. We just initialize that with zeros. And then if it's an embedding, we're going through again an init normal of a mean of 0 and standard deviation the same as the linear layers. You can choose to mess with these and see if your model converges faster. Now we'll go through the forward loop, and then we'll probably park aside the generate once we get to the sampling. So what we are going to get as part of the forward propagation is a batch, and each batch will contain a sequence of tokens. Now what I want to ensure is that the sequence of tokens that we get at each row does not exceed the context window. Now if it does, in this case I've chosen to raise an error, but if you want to let this pass silently, what you can do is clip those sequence of tokens as per the batch size. So you can do something like if t is greater than equal to, or you may even need the if because you're clipping, right? So T can just be minus self.block size and then a colon. So it ensures it takes the last 128 tokens and does not spill over. I've chosen to raise an error. Now, for the pos variable, I'm doing an a range of 0 to t. So I'm getting a placeholder for myself for the position. And then from there, this is going to give me all of the positions. So for a batch, again, if you have a sequence of tokens, one has 3, one has 5, one has 7, it will give me a matrix that is full of 0 to 5, 0 to 7, depending on your sequence length. It literally just gives me the integer positions so that I can use them to compute the positional embedding. I unsqueeze it. So squeeze reduces the dimensionality, unsqueeze introduces another dimension, just helps with the math, adding the dimension. So I'm going to take my list of IDs and then pass them through the token embedding, pass them through the positional embedding, and then I'm going to add them up, drop out if any. And then once I have the embedding with me, I'm going to pass them through however many blocks I've configured here. So in this case, only 2. So again, the variable needs to be the same is an important aspect of this, because the input to the second block will be the output of the first block. So you want to keep the variable names consistent here. And then once it goes through the blocks, it goes through a layer normalization. Again, ln_f is nothing but a layer norm. And then from there, we use the head, which is the linear layer, to get our logits. Now, if it is a training loop, there will be targets associated with it, and we can compute our cross entropy loss against the logits and the targets. Otherwise, a none will be passed back, which essentially indicates we're trying to inference and not train. So what we will do now is go inside each block and open it up. So this is what a block looks like. And this is essentially the block that we have seen before in our part 1. So this is the part I'm talking about. This one is a block. A block consists of addition and normalization layers and a multi-headed attention, which again opens up over here, which leads to a scale dot product attention here. Now I have chosen to add the layer normalization before we apply the attention. You can choose the reverse as well. So the input comes in, it goes through a layer normalization step, and then it passes through the attention mechanism, which in this case is a causal self-attention mechanism. And then the output of that is added to the original input. This is where the skip connection happens, right? So the input is added to the input layer normalized and then passed through attention. So that's your skip connection right there. And then this is in turn passed through another layer of normalization, and then a feed forward network, and then again a skip connection component to it. And then finally you return the X. So this is what a block looks like. I'll correlate this with the diagram again for perspective. So we go through the multi-headed attention, or the causal self-attention as we call it. The X, or the input, is passed through and added to the output of the masked multi-headed attention, and then it propagates like so till it hits the feed forward network, and then it's further added and normalized. So the input to the feed forward is added and normalized with the output of the feed forward here as well. Now, if we open up the causal self-attention mechanism, things should be extremely familiar. So we are again asserting, like the previous part we did, that the number of heads is evenly divisible by the embedding length that you have set. And then from there, we're going to take a QKV, which is 3 times the embedding length, and then go through the split over here. This is just to copy paste the exact same thing that we've seen before. And then finally it goes through a scale dot product attention, a PyTorch implementation this time, and then the transpose contiguous view. which then goes through a projection layer to return the Y. So again, if I were to correlate with what we've seen before, so it goes through the QKV. All of these are just one linear layer, and then we choose to split it, and then the scale dot product attention concatenated with a linear layer. So on the feed forward network, it's just a simple sequential neural network with a linear layer that blows up the embedding length by 4. So n embedding comes in 4 times. N embedding is the number of neurons in the hidden layer. It goes through a Gaussian error linear unit activation. It's just a smoother version of ReLU. ReLU has hard cutoffs, which again messes with the stability of the training. And then it goes back to the same linear, but in reverse, almost resembling an autoencoder, and then a dropout. So once I have that, I hope everything here starts making a lot of sense, so we can get back to our train.py. So we've gone through the tokenizer, the byte dataset, and the GPT model. So we can proceed to how our training loop looks like. Now, if I pass the compile argument as part of the training, I will compile my model. Now, in a sense, a small sidebar over here is Torch became popular because it was dynamic and it was much more debuggable, eager execution, right? So you can build the neural network and debug things along the way, literally with the inbuilt Python PDP, Python debugger, which TensorFlow did not have in the initial years. It was just a session graph that was very hard to debug. So somewhere with torch.compile, over the years, Torch has moved closer to TensorFlow 1.0's initial behavior, and with TensorFlow 2.0 introducing eager execution, TensorFlow went back to more simulate the behavior of Torch. So I think somewhere these two packages are converging, and I don't subscribe to the PyTorch versus TensorFlow cult debate, as you want to call it. I think you should use the right tool for the job as well, right? So you can choose to compile your model. That makes it a static graph. Again, it can sort of find its own set of optimizations by fusing layers and making things more faster, basically. So from there, I'm declaring what my optimizer will be. In this case, it's an Adam optimizer. So pass the model parameters and the learning date, the betas, and the weight decay, again, pass through an argument. Now, this next one is going to be interesting. So what we are going to be attempting is an automatic mixed precision training. So PyTorch is aware of what all modules that you're trying to use in your neural network. So especially for the linear and the convolution layers, it understands the fact that reducing the precision of the weights from FP32 to FP16 will significantly speed up training. But what can happen is we can encounter what is called a vanishing gradient problem. So if you take an FP32 weight and then approximate it to FP16, you might lose a lot of precision and the weights can go to 0, and we call it an underflow problem, a gradient underflow problem. In order to tackle this, what PyTorch does is it provides us with a gradient scaler. So what it will do is scale the loss with the help of this gradient scaler, back propagate, and then scale the loss back so that you don't need to adjust the learning rate yourself. So in this way, your gradients won't underflow and your training will be stable. So you have slightly more perspective here on the PyTorch documentation itself. So if the forward pass for a particular operation has float 16 inputs and the backward for that operation will produce float 16 gradients, we'll have small magnitudes representable by float 16. These values will flush to 0 or the underflow, so the update will be lost. Now to prevent this, it will scale again. Gradient scaling multiplies the network's loss by a scale factor and invokes a backward pass on the scaled losses. gradients flowing backward through the network are then scaled by the same factor. In other words, gradient values have a larger magnitude, so they don't flush to zero. We'll see elements of this in the code. So we are pre-declaring our scalars so that we can have stabilized, non-vanishing automatic mixed precision training. We set our best valuation to float of infinity, time step, and then set the model to train, and then the training loop starts. So we'll go from step 1 to however many steps that we have configured. So for each step, we're going to get a random batch from the training data, because this is a training loop. Our batch size is 32. So we get the corresponding X and Y, and again, quick refresher. So get batch literally returns the X and Y with all the list slicing gymnastics that we've gone through over here, right? So we get a batch, and then we wrap it up with the AMP context manager here. So we say torch.cuda.amp autocast enabled. We go through the forward propagation. Now again, doesn't matter if you're even using a CPU and this won't apply, but it's nice to understand how a real world training actually happens. So we go through the model, and now this will just invoke the forward propagation of the GPT model with all of the layers that we've already discussed. So we have the loss over here because we have chosen to pass the targets, and then optimizer.zeroGrad so that the gradients can be set to 0 and they can be computed. Now, this is where the magic happens. I do scalar.scale the loss and then do a backward propagation, right? So this is an important step. Again, this is only because we're doing AMP. If you don't choose to do AMP, good luck blowing your memory and not using or not introducing this unnecessary complexity. If the gradient clipping has been configured to be greater than 0, and this is the other side, this is the exploding gradient problem, where I'm passing a gradient clip, and if that is set to greater than 0, which it is, the scaler will unscale and apply that to the optimizer, and then Torch has a nice clip grad norm over here, which again acts on the parameters, making sure that it clips the gradients corresponding to each of the parameters if they are greater than that particular value. So in our orchestrator, I think we pass 1, or by default it's configured as 1. So the gradient clip here has been configured as 1 so that we don't make dramatic updates to our weights. So it will get clipped, and then finally the scalar.step with the optimizer, and the update will happen. So just a small step that we had to introduce to sort of show you how you can train your models with AMP. Applies to pretty much all settings. It doesn't have to be localized to LLM training in general. Now, every 50 steps, we will log so that we can track what are corresponding losses and whatever metrics we are interested in, what they are. Now, if I'm to configure this eval interval, which I've set it to 100, so every 100 steps, I will estimate my loss, print it, and if that loss is less than the best loss that I've seen so far. So essentially think in the first step, this will always be true because we've set the best val as plus infinity. So the best val will be set to the validation loss that we're seeing right now. The model will be saved in the checkpoint path. So we have the runs folder over here where the PyTorch weights will be saved. If the directory that you've configured is not present, we'll just create it. And then we're saving a bunch of these parameters with the model state dictionary as well, so that we can exactly reproduce our checkpoint when we are loading our model. So with this, we've completed the training loop, and now we will sample. So if you've configured the sample every parameter, then we will actually sample and print stuff out the console based on whatever parameters that you've configured, right? So let's say your sample every is greater than 0 and you've set it to 100. So when we hit the 100th step, this will get invoked, And this is again a way to get the a list of indices that serves as a seed for our prompt. This is the exact same implementation that you have already seen in the get batch API. So we start from the 0, we go till the training length minus the block size, so that we can sample a block size, and then we take an item, and then from there we take a subset of the training data from that integer to the block size, unsqueeze it so that it matches the dimensions, and this becomes our prompt to generate. And then we do model.generate, we set the seed, set the max new tokens. This is again coming from an argument. I think this is set to 200 by default. We're setting the temperature top K, and then we're decoding everything back to text and then printing it. So finally we're saving the model once we train it, and then this should just be over the training loop, right? So what we'll do now is go deep into how the generate happens. If you remember, we had taken the model.py and skipped the generation step entirely, and this is where it's sort of useful. So when you load the model from the checkpoint and are trying to generate a bunch of tokens, you can set certain parameters. And what I'm interested in explaining the most is the temperature top K. Even if you've heard it and you know what it does, it'll be interesting to explore how these things are achieved. So we have the generate, and from the utils, we'll explore the utils in a minute. We've imported the top K top P filtering. We are setting the model to eval, and now if you do not pass the prompt, so in this case from the train.py, I am passing a prompt, which is nothing but the seed. But if you invoke the generate method separately from another module and you send an empty prompt, I'm just filling it with the default list of prompts so that generation happens anyway and nothing gets errored out. So in our case, it won't be an empty prompt. So for the max number of tokens that you've considered, I'm going to clip off the list of IDs that you have sent me by the context window. So again, if you send me a large enough prompt, I'm just going to start from the end and go back all the way till my block size number of tokens are satisfied, and then clip the number of tokens and then just process them. So from there, this list of IDs goes through the forward propagation, which will give me the logits. And since I'm only going through the generation, the loss will be none. So if you look at the forward API, takes a bunch of indexes, forward propagates them through the model, and then returns the loss if only the targets are there, otherwise returns a none. So I'm not interested in saving it. Now, here is where something interesting happens. So we take all of what we get back and then we slice it like so. We're taking the 0th dimension and the second dimension as is, but the first dimension we're only taking the last element and then doing something to it. Now, in order to understand this, we really need to understand how logits are returned given a batch, right? So now let's say you have a batch of tokens. So let's say this is your batch, right? Now, when you forward propagate this batch through the model, what it returns is actually, so if you pass, in this case 4, in this case 3, in this case 5, what it gives you back is the exact same number of tokens, but just right shifted. So if the position of this token is 0, 1, 2, 3, then the predictions that you will get for this corresponding sequence is the prediction at position 1 given the token 0, the prediction of position 2 given the token 0 and 1, the prediction at token 3 given the token 0, 1 and 2, all the way till goes till 4. So since we have 4 tokens over here in the input, it will also give me 4 tokens in the output, and this is the extra token that I'm interested in. So again, if you have configured this to be 200 output tokens, it will give you 200 more tokens here, but it will also preserve all of what you gave in the input. Again, just right shift it. This is an important point to understand. So that's why the batch is a dimension, but then for every sequence, it also returns the prediction for every right shifted position. So that's the second dimension. And for every position prediction that you get, it will actually be a long list of all of the vocabularies that we have configured. So in this case, we have 256 tokens, which is our vocab size. It will return the logits. So from here, what we will do is we're going to make a note of the batch dimension and each and every token. Now, if you're going to sample these tokens one by one, which is what happens in an LLM, right? So if you've passed 0, 1, 2, and 3 as an input, what will happen is the fourth token will get, you'll get as output, and then the entire sequence will be passed, and then from there the fifth token will be sampled and so on, right? So when you want to do that for a particular prediction, you just want to grab the last token in the sequence. That's all you're interested in at this particular point, right? So that's why when you're looking at this, so we are only grabbing the last token, which is the literal prediction that we've gone through. So again, we're doing predictions given each token. So we're running this loop for each new token prediction, and we are only interested in the latest token, which is nothing but the prediction token. Now this prediction token will have, in our case, 256 logits, which is our vocab size. And then I'm scaling it by the temperature parameter that you have passed. Now note that the implementation of the temperature, because it's a division operation, is a max of temperature and a very tiny number. This is just to protect the zero division error if you pass temperature as 0. Now, as far as my understanding goes, and I can't confirm it because it hasn't been brought out, but the closed source LLMs that you use, the Geminis and the OpenAI chat GPTs of the world, have a similar implementation, which is why even if you set the temperature to 0, they do not guarantee a greedy token selection approach. It's based on a best effort basis. So the proof for that is I've literally opened the Gemini API docs. So the temperature is used for sampling, blah, blah, blah. Where it says is lower temperatures are good for prompts. A temperature of 0 means that the highest probability tokens are always selected. In this case, responses for a given prompt are mostly deterministic, but a small amount of variation is still possible. And I think it's because of the 1e-6, a very tiny number that we've passed. When this happens at scale, there is a possibility that there will be slight variety in the generation, even if you set the temperature to 0. So we've done our best to adopt what might be going on in all of these industrial strength implementations. So we're going to take the logit and diffuse them by temperature. Now you can easily see that the higher the temperature, it gets the logits gets diffused more and more. So lesser probability tokens will have relatively higher probabilities now, or they'll have an even playing field when you're trying to sample tokens. So that's why for anything creative, it's recommended that you use a higher temperature. So it will sample more unseen tokens in the training data. But if you want to be conservative, really use a low value for temperature. And then from there, it goes through the top K top P filtering that we have configured. We'll look at this in a minute, the implementation. So we've got the utils.py, and this is our top K top P filtering mechanism. So what we have is we're getting the logits, and we need to have a filter mechanism. So let's understand the top K top P first, and then we'll probably come back to the implementation. So what we have is at every step, you will get 256 predictions. So for each token that you want to select, you have a candidate list of, in our case, 256 tokens, which is the vocab size. Now, what is a top K filtering is an extremely easy thing to understand. So if you set the top K as 10, it will sort it by the probabilities, reverse sort it by probabilities, choose the top 10, and then sample any one from this distribution of 10. So instead of sampling from 256 tokens weighted by their probabilities, it only samples from the 10 that you've configured as top K. Now, the top P can be set to something like a 0.95, for example. What happens here is, again, you reverse sort your list of tokens, list of candidate tokens by the probabilities. And then what happens is you want to compute the cumulative sum. So let's say this is 0.1, this is 0.2, this is 0.01, and so on, all the way. Everything will sum up to 1, because we're looking at a softmax distribution. And then from there, the idea is to reverse sort it first. So the 0.2 comes up first, the 0.1 then, the 0.01 then, and then the rest of it. And then you calculate the cumulative sum. So at the first step, it will be 0.2. At the second step, it will be 0.3. At the third step, it will be 0.31, and so on. And then you want to take it all the way till 0.95, 0.98, and then maybe we hit the 1. So the idea is to cut off here, since our top P is 0.95, and then sample only from this distribution, and then discard all of this, all of the long tail below. So that's the core idea of top P, top K. Let's understand how this is implemented in PyTorch. So in PyTorch, I'm first implementing the top K if configured. Even if it is or not, I'm also going for the top P implementation. So first things first, I get my logits and take a clone of them. Now, if the top K is not none, and the top K is less than the vocab size itself, so by mistake, if you've set the top K to be north of 256, nothing will happen here. If it is less, then it will get filtered. So Torch has a nice top K function where I can pass my the copy of my logits, and then pass the number of tokens I want to filter out from them, and it automatically handles the sorting and the filtering. So from there, what you essentially want is you want to take the top values and those that are not the top values. So you take the cutoff here, you set it to float of minus infinity. Again, this is a neat trick that we have seen, so that when we pass it through softmax, it just becomes 0. So that's the top K implementation, easy enough. Now for the top P, we're doing a little more custom hand wavy implementation. So we're first sorting them in descending order, and then from there we'll need to compute the softmax, and then we are computing the cumulative sum of the probabilities. We are creating a mask off of the cutout that you've specified in the top P, and then we're setting the first token to false, so that we make sure at least one token is selected. So if you set your top P to be a very small number and not even a single token is selected, we make sure that the first token is selected. And this is again a very cool implementation in PyTorch, where you can take a tensor, and it doesn't matter how many dimensions it has, 2 or 3 or 4. You keep the rest of them as is, and you only deal with the first index of the last dimension. That's all you're interested in, right? So with that, we apply the mask. So we set everything to float of minus infinity. Again, this is the same as top K. Now, in top K, we had set certain tokens as minus infinity. And then in the top P also, we are setting certain tokens at minus infinity. So we're going to just combine all of that. This is the scatter step. So from here, we are doing taking a replica of the filtered matrix, filling it up with minus infinity, and then using torch.scatter to stab the values of minus infinity with the sorted logits and sorted indices that we've got. So what does scatter do? So it writes all the values from the source tensor at the indices specified in the index tensor. So we're using the tensor.scatter. So this will be the source. And then from there, I pass on the indices where I want to write, the dimension along which this is supposed to act, and then it should just work out. So I want to do it along the dimension 1. These are the indices, and these are the values which will be imposed upon this filtered, which has been initialized to be minus infinity everywhere. So it returns the filtered matrix after the top K, top P implementation. So you see, we're done covering this step. And then from there, we take the softmax of the logits to get our probabilities. And then now we know that these are the filtered versions of those probabilities where the top P, top K has already been applied. So we're going to sample from this distribution based on these probabilities. So I passed the list of probabilities, and for the tokens that have not been selected with the top P, top K scheme, the probabilities will be 0. So we've ensured they'll never get selected. I only want to sample one from here. So in implementations like beam search, you might want to sample more than one. We're not covering beam search, left it as an exercise. So from there, what you want to do is you want to take your original prompt, and then you want to take your next ID prediction and concatenate it with this, and then finally return the index. So if I come back to train.py, a lot happened between setting the prompt and putting it for generation, right? So I've got the vocab size back now. All I need to do is decode and print them out. So without further ado, we'll run and see how this looks like. So I'm already in my part 2 folder, and all I have to do is Python orchestrator.py. So it first takes the train.py and runs it against this data set. So for every 50 steps, we can see that the loss is going down. So our training is working well. And then at every 100 steps, a sample gets generated of how the text looks like. And you'll see that after every 50 steps, there's a slight qualitative improvement in the generation because, again, the loss seems to be going down steadily, right? So we went from 1.2 to 1.1 and so on. And we are saving the checkpoints along the way. The checkpoint saving strategy is something that we will go through in part 4 as well. So once we have the training complete, we're going through sample.py, and for that we've provided an English prompt, which doesn't make sense, but anyway, all we wanted to see was the generation happening, and at no scale can we expect a 2-layer transformer architecture to work, right? So we're going through the evaluation loss. And for this, I think we've skipped the estimation of the evaluation loss. So here you can see that I've got an estimation loss after every evaluation step that we've configured over here. So you'll see that at the evaluation interval, we are trying to estimate the losses. So the way to implement that is put the model in eval mode first, and then with no gradients, we just want to forward prop. For however many iterations that we've configured the evaluation for, we'll get a batch, we'll forward propagate it. And since we know our Y's, we will get the loss back. We don't care about the predictions here. We're just interested in the loss. And then we append the loss to the list that we've configured here. And then for every evaluation iteration, we're just going to average it out and then put the model back on training so that our model can continue training, and then return. So that's our estimation of the loss that we had sort of skipped through. So this is what we have. This brings us towards the end of part 2. So hopefully we've covered all the topics in great details, and I hope you had a lot of fun doing it. Thank you. Hello and welcome to part 3 of the LLM from Scratch series. And in this part, we'll look at what we have implemented and try and modernize the existing transformer architecture. So step by step, we'll introduce all of these concepts and also look at how we can put these together in code to achieve one of the more modern forms of the LLM architecture that we have. So first things first, we'll start concept by concept. What I want to do is spend some time doing some theory, picking up each of these concepts apart and explaining them separately, and then we'll figure out a way how to put them together. So first, we'll look at RMS norm, or root mean square normalization. Now this is going to be an alternate to the layer normalization module that we are doing. And what this does is normalize the vector, the incoming vector, by the root mean square of it. So it's literally divided or multiplied by the inverse of the sum of squares, the square root of the sum of squares, right? So this is the formula. So the RMS of x is going to be the square root of the mean squared plus an epsilon, and this we add just a very tiny number to avoid zero division error. And so x is divided by the RMS. Now the g term here is a weightage term, which in this case we'll just use torch dot ones. So all of them will have the same weightage. So here we can see the incoming x is first squared and then the mean, and then the epsilon is added and then the square root is taken. It's just one chain of PyTorch command, and then from there it is divided by x and multiplied by the weights, which again has no effect in this scenario. So that's RMS norm. Now why are we using this? It's slightly more efficient because these operations eventually in the GPU can be fused together, and we don't have to keep track of mean and variance as in the layer norm. We'll just have to do this in one shot. Now the second thing I want to discuss here is Swiglu activation. So in modern LLMs, the ReLU or the GELU activation that we've seen before is not used anymore, especially in the feed-forward network. What we see is the swish activation of the Swiglu is what is called. So you have an incoming x, and it goes through a linear projection to get A. So W1 is a linear layer, and then the x also goes through a separate W2, which is another linear layer, and then the activation is applied upon the output of propagating x through W2. So that's in this case the SILU activation function, or the sigmoid linear unit, which is literally the number multiplied by its sigmoid. So as you can see here, the SILU function is also known as the swish activation function, which is the number multiplied by its own sigmoid. This is what the curve looks like. And then optionally, we can go for a dropout. So this particular module is what we're going to use going forward for our feed-forward network in our transformer architecture. So we've covered RMS norm and Swiglu. Now the other thing that I wanted to explain before we could dive into implementation, and there are a couple of more of these. One of them is KV cache. So the idea is pretty simple. In the core transformer module, we have a Q, we have a K transpose, which results in a QK transpose, which is then multiplied by a V to get our final attention weights. So let's say token 1 comes in, and what happens is it interacts with the transpose of token 1 pushed through a different set of linear weights. And then what we have is the token T1 interacting with the token T1. That's the outcome. And then in the V, we also have T1, which then results in the attention 1. Now, the A1 is then further propagated through the transformer block to finally get a token, which then feeds into back into Q. Now, the whole idea is before KV cache, the token 2 comes in, and the entire processing from token 1 to token 2 and all its interactions, they were happening in one shot redundantly. So the idea is, if I've already processed token 1, can I cache it and save a bunch of computation? So what we do for that is we'll cache in the K component and the V component, hence literally the name KV cache. And then all we need to do here is build a new row. And then from there, we do not need to store the attention output here, and we do not need to store the queue here. So here, when the token 2 comes along, I can literally replace it here. And then all I need to do is build my KV cache with one more element. And then here, the T2's interaction with T1 and the T2's interaction with T2 is what I need to store. So I'm literally adding a row here. And then from there, T2 goes here. And this literally can be replaced by A2, which then eventually gives me token 3, which again I'm going to use to build my K cache and my V cache. And then I'm going to add a row with T3's interactivity with each tokens. So this literally is what is called a KV cache, and it saves a bunch of computation. Now we've built a small module here to kind of compare the difference between what happens when you use cache versus when you don't. So stay tuned for how this is implemented in code and what are the actual performance gains. And this especially applies obviously in inference mode when we're trying to generate token by token. So it's an efficiency in the inference step. So we're going to look at KV cache. Now the next topic I wanted to cover was grouped query attention. Now before we could do that, we actually have to understand KV cache, the non-functional aspects of it, and what is the impact of using this. So let's say I'm going to cache the K and the V, so that's 2 of them I need to cache. And then let's say inference happens at FP16, so I've got 2 bytes for each floating point number that I want to cache in. Now from there, let's say a typical 30 billion parameter model will have typically 48 layers. So I literally need to do this for 48 layers. And then from there, inside, we're talking about manipulating embedding lengths as part of the KV cache. So let's say this will be 7168 embeddings. And then let's say we are trying to do a very modest sequence length of 1000 tokens. And then finally, let's say we're trying to do a batch size of 128. Now with this setting, if you just plug in the numbers and multiply them, and I think the batch sequence, the sequence length, the embedding length, the number of layers, the precision, as well as one for the K and one for the V is all that we need. I'll fix it in retrospect if I'm missing anything here. So this will you do the math, it will come down to about 170 gigabytes. So what you're doing as a cost of efficiency is actually sacrificing on a lot of memory, and eventually you will have to take these kind of decisions over and over again, because memory and compute are always a trade-off. So this presents a problem. So KV cache wanted to solve the computation problem, but introduced a new problem, which is the memory overhead that is required to build it. So in this case, what we are next trying to introduce is how do we reduce our KV cache and how do we make the attention module more efficient. So in this case, we are using multi-headed attention, where every query head maps to each key head, which then is interacted with the values head. Now, instead of that, one extreme proposal can we do multi-query attention, where all the query heads map to one single key head, which then goes to one single value head. Now, this is where we see the most gains. So it's most efficient, but also there's a significant accuracy loss. And this sort of serves as a nice middle ground where I can take one key head to tend to one group of queries, and hence the name grouped query attention. And this can be 2, this can be 4. In this diagram, the mapping is for 2 queries going to one key and one value. So if you do this smartly, you will notice that picking the right group size can literally take that 180, 170 gigabyte and has the potential to almost reduce it by an order of magnitude. So this is an important implementation that we're going to go through as well. So that's grouped query attention. Now from there, we introduce another optimization to the attention mechanism, and that's a sliding window attention. So we're only going to focus on this and this. We're going to skip the history lesson of how this came to be, but I'll drop in a word or two about attention sync. So what we are using is dense attention, where the current token, in order to be tended to, can go back and look at the entire context window that is available to me, right? So this is the dense attention mechanism that we are already aware of, and this has a quadratic complexity. That's the problem. So if I go over here, the streaming LLM, as they call it, is literally sliding window attention with an attention sink. So what we do is, we always use the first few tokens. So the first few tokens are always part of the context window, and then we use a sliding window attention for the rest of this long tail. So we have first few tokens always getting used here, and then there's a sliding window over here. Now in this diagram, it's depicted that the attention sink is literally one token, but in practice, we tend to use the first few tokens as the attention sink. Now, intuitively, why is this called the attention sink? Now, it turns out that if you take the entire context window and then just shrink it down to this sliding window attention context window over here, then what happens is, let's say I do not want to pay attention here and I want to pay more attention here. What happens is, it's bound to disperse its probability / attention across these 3 tokens only. Now that leads to a lot of errors and a lot of catastrophic forgetting. So what the authors have proposed here is they'll use the first few tokens and they'll anchor it always in the beginning of the context window. So what happens is, as you're sliding through the context window, if you do not want to pay unnecessary attention to a particular token, you can quote unquote dump all of the probabilities out to the BOS token or the beginning of sequence token or the initial token. And that way you can pay the right amount of attention to the right token as you're sliding across. So that's one part of the intuition. The other part of the intuition is, I want to compare the sliding window attention mechanism to the receptive field of CNNs. So let's say you're trying to process an image through a CNN, and layer 1, it looks at a particular receptive field. Now layer 2 will actually look at a receptive field of layer 1, and layer 1 has looked at the receptive field of the source image itself. So what layer 2 is looking at is actually a summarized and a condensed version of a bigger receptive field that L1 has gone through. Let me try and explain this with an example. So let's say you have the incoming sentence, the cat sat on a mat. Now, what happens if we slide this through the layer 1 of transformers? So obviously, the first element or the position will just pay attention to itself. The second part will look at both these interactions. So it will have information or interactivity stored about the tokens the and cat. And then third, it will have the cat sat. And now, if I'm not using the entire context window or clipping my context window to only, let's say, 3, the sliding window attention is 3. Now it will look like we're starting to lose context. So the cat sat on a, then on a mat. So compared to using the dense attention mechanism, it looks like we've lost a lot of context. But this is only in layer 1. So what happens in layer 2? We have so just the first token interacting with itself. Now in the second part, we have the cat interacting with the. So essentially we have some information about the cat. Now in the third, we have the interacting with the cat, interacting with the cat sat. So again, essentially we only have these 2 or 3 tokens to deal with. But look at what happens here. So at this stage, if I'm going to tend to only 3 windows, so my window size is 3, I've already covered the cat sat on. Now what happens in the next step? I go from these 3 tokens. So I'm essentially processing the cat sat on a. So by the time I get to the next layer itself, even though my sliding window attention is of size 3, I'm capturing the interactivity of 5 tokens here, right? And again, for simplicity's sake, each word is a token here. We all know that's not true. So when I get to the last stage, then all I'm using is just losing, it's just 1 token. So you see, by decreasing the sliding window or decreasing the context window and having a sliding mechanism in place, as I go through subsequent layers, and I'm sure by the time we get to L3, I would have captured a lot more context, probably the entire context, right? So the core idea here is, since we have a lot of layers in our transformer, through the receptive field mechanism of propagating layer after layer sequentially, I'm still capturing a lot of information, and I can live with a sliding window attention mechanism. So now if I come back to the whole KV cache situation, what we are going to implement eventually is called rolling buffer KV cache. So we are not interested in implementing a full-blown KV cache. What will happen here is I would have cached tokens T1, T2, and T3. Let's say there are 3 attention to, sync tokens, right? And then in the next step, I will do T4, T5, and T6. And then when it goes to the next step, my T1, T2, and T3 will remain constant. But through a sliding window mechanism, I will actually evict token 4. And then what will be left in my KV cache is T5, T6, and T7. Right? So this is going to be my KV cache. And you see where this is going? This will always be constant, while this has a sliding window operation where tokens in the middle get evicted. So this is going to be a rolling buffer KV cache. And this again, if implemented correctly with the right hyperparameters, can further reduce your KV cache by an order of magnitude without compromising a lot in the accuracy. So that's the core idea of sliding window attention mechanism. Now, the next thing I want to discuss is how we're not going to use absolute positional embeddings anymore in our transformer architecture. So first of all, the transformer by itself is position invariant. So that's a problem, especially in language, because the cat sat on a mat and the mat sat on the cat are two different implications, right? So we had to introduce an absolute positional embedding for that particular reason, to preserve or to embed positional information in some meaningful way. Now from there, what I can say is the absolute positional embedding has a problem, which is that each positional embedding that I come up with is independent of each other. So if token 1 has a positional embedding, it is different than token 500, it is different than token 2, right? So this presents a problem where the relative position matters a lot. The distance between two tokens should be pivotal in deciding the amount of attention I want to pay across those tokens, right? So enter relative positional embeddings, and what this is trying to capture is a bias term that literally represents distance. So let's say if you have, I'm representing each row as a token. So I'm going to introduce these biases. So I have B0, B1, B2, and then B3, and then T2 goes from B minus 1 to B0 to B1 to B2, and then this goes from B minus 2 to B minus 1 to B0 to B1. Now, what is happening here is B1, for example, is trying to represent the bias associated with distance 1. Let me explain that with an example. So if I have 4 tokens here, now the distance between A and B is going to be represented with B1, B and C is going to be represented with B1, and C and D is going to be represented with B1. So any tokens that are one distance apart is going to be represented by this bias term. Now the distance between A and C, B and D is going to be represented with B2, and the distance between A and D is going to be represented with B3. Now the problem is, when every time a new token comes in, you'd actually have to add stuff to T1, T2, and T3 as well while you're building this bias matrix, right? So in KV cache, the desired behavior is that if I have processed token 1, I'm going to cache it and I'm never going to think about it forever, right? So what relative positional embeddings is forcing us to do is actually go and modify each and every caching mechanism that we want to have for. So if a 4 token comes in, I'll have to add a B4 here and a B3 here and a B2 here, and then add my row for token 4 here. So we've got -3, -2, -1, B0, and then like so, right? So what we want to do here is essentially is that if I've processed the positional embeddings of token 1, I just want to be done with it. I never want to revisit it. And that's why this is more of a transitional term to understand rotary positional embeddings. And you can see that the T5 bias, which uses relative positional embeddings, is quite slow, although slightly more effective than absolute positional embeddings. Because it captures the relative positional embeddings, it's slightly more effective, but again, as the input length increases, it becomes slower and slower. Now, rope is the mechanism which captures the best of both worlds. It captures the stability of the absolute positional embeddings, but it also captures the relative distance in a meaningful way that relative positional embeddings was offering. So combining these two together, rope will solve both of our problems of stabilizing KV cache as well as capturing relative distance. So quick intuition of how that works. So let's say you have a 2-dimensional word vector here, and this is called let's say the vector for dog. Now, depending on where this token appears in the sentence, so let's say it appears here. Now, what rope is trying to say is that there's an angle theta with which I'm going to rotate the vector dog, And this is going to be, the M is going to be literally depending on the position of the token. So very intuitively, if dog is the second token in the sequence, then I'm going to rotate it by 2 theta, and this becomes the vector with the positional information embedded. So if a new token comes along here, let's say, then its rotation will not affect dog's rotation. So I don't have to go back and fix anything over here. And so let's say chill comes out to be here. And I can even capture the relative positioning information through the angle through which a particular new token is rotated, right? So every token that comes along gets positioned in this n-dimensional vector space and is then manipulated or rotated through an angle of theta weighted by the positional information depicted here by M. And then that will end up representing the positional information of that token in absolute terms, but also relative to other tokens in this n-dimensional space. So that's the intuition behind rope, and this is how it's implemented. So what we have here is a notional representation. So this is what it should look like, and the way it's done in practice is that the incoming vector, let's say you have a vector of numbers here, they're taken 2 at a time. So this particular operation is applied to these 2, and then this particular operation is applied to these 2, and this way it happens in pairs, right? So each pair here is represented by this, but we never want to build this matrix in practice because it's just too inefficient. That will blow up memory. A simpler, cleaner way to represent it is down below, where I have x1 through xt, and then I have this inverted sign, and then I've got the cos here and the sine here. Now what we can do here is we can cache these up front, the cos and the sine. So this starts getting called the rope cache. So we can build a separate cache, and this is not to be confused with KV cache. I can pre-compute, because this is not going to be something that will be learned over time, but I can pre-compute it for my entire context window for all positions that I'm going to see, the sines and the cos, so that every time an x comes in, a vector comes in, I'm just going to get, instead of computing the cos of each angle every time, I'm just going to get the corresponding values from my rope cache and then multiply it with the corresponding numbers to get my output. Now, another aspect of this is while in the previous transformer, the positional embeddings was incorporated before it went to the block. In this case, we are going to apply rope after it enters the block and on Q and K separately, right? It is not applied on V, it is applied on Q and K. So with that, I think we've gone through a bunch of these concepts, and we are ready to implement and see the implementation of a more modern LLM architecture. So the aspects that we saw is RMS norm, Swiglu, KV cache, group query attention, sliding window attention with attention sync, and finally rope. So I hope kind of these 5 or 6 new concepts we've picked apart and try and understand them separately. And now when we finally look at code, everything should start making sense. All right, so let's go through the code. These are the stuff that we're interested in implementing. As always, the entry point to our part 3 will be orchestrator.py. We've got a ton of these implementations here for the different modules that we've discussed. So first things first, I'm going to run a bunch of tests just to see I'm going well. And then I have this generation mechanism where, so since we've already spent a lot of time discussing the changes in the architecture, in this part we won't be training a model. we're literally going to initialize it with random weights and see whether it runs or not, and how the forward propagation happens and how the generation happens. Compare it with or without using KV cache, what's the impact, so that we can just hyper focus on these aspects and not convolute it further with some things that we already know, like the training module part, right? So we're going to do demo generate.py. We're going to use RMS norm. We're going to use rope. We're going to use Swiglu. We're going to use sliding window attention of 64 with a sync token size of 4. So essentially our context window, which was 128 before, just became 68, and I'm trying to generate 200 new tokens, right? So with that, we can get to demo generate.py. This is what it looks like. So some of the arguments we've passed already. The group size is for the group query attention. So I've taken a default of 2 here. So for every 2 query heads, there will be 1 KV group. That's what it means. So we've got RMS norm, rope, Swiglu, sliding window, sync, group size, tokens in CPU. And then from there, we choose the device. We're still using the byte tokenizer. And then this is where the model magic happens. We'll get to that in a minute. And then from there, we're making a dummy prompt, just hard coding a dummy prompt. And then we'll generate this with and without KV cache, and then compare the outputs in terms of quality and time. So let's get to the GPT model in a modern implementation first, and then we'll come back to the inferencing part. So here I've got the GPT modern implementation. So if we go through the hyperparameters, then we have vocab size, the block size, the number of layers, number of heads, number of embeddings, whether to use dropout, whether to use RMS norm, Swiglu, rope, and then max pause. Again, this is something that we'll use to build the position of the rope cache. Sliding window, attention sync, NKV head. So I've renamed the group size to NKV head here. This is literally going to be the group size. So this is going to be interpreted as the group size. So I'm passing the args.group size in demo generate.py to the NKV head, right? So what are the different components in the init phase? So we've got the block size, we've got the token embedding, we've got the position embedding, but we're not going to use it. So it's just there for display purposes, right? So we're not going to use the positional embeddings in this space. We've got dropout, and then blocks is again an all too familiar module list, but this time we're going to use the modern transformer block. And then if RMS norm is turned off, we're going to continue using layer norm, but if it is turned on, we're not going to take any action. That's why it's nn.identity. And then finally, our head will be the linear layer as always. So we can take the forward propagation here and then go back to how the transformer block modern is implemented. So the indices come in terms of batches, and each batch has a sequence of tokens. As always, I'm checking if the sequence of tokens is less than the block size. You can again choose to clip it if you don't like this particular implementation. So I'm building my positions here. So the positions will be nothing but an A range of 0 to T. So for each sequence that comes along, let's say sequence 1 has 30 tokens, so it will go from 0 to 29. The idea was to use it with positional embeddings, but that's turned off now. You can turn it back on. And then we get to the KV cache part. So what I'm saying is we're iterating through the blocks. So this is a forward propagation, and each block we're going to iterate through it in this for loop. So I is the index of that particular block, and the BLK contains the block itself, which is the transformer block modern. So with the cache, we are saying none if KV cache list is none, else we pluck out the particular index from the KV cache list. So the idea is KV cache list is a list of KV caches for each layer in our transformer. So if I have 6 layers, this will be of length 6. So depending on which block we are accessing, we want to pluck out the right KV cache and use that as input to our block. So to our block, we are sending X, the thing that we want to compute. We are sending the cache that we've previously plucked out, and then we are sending the start position. So again, I've kept this because I wanted to understand the interactivity between the sliding window and clipping of the block size, etc. Most of the times, for all intents and purposes, this will be 0. We'll see if this has to be different. I think in some cases the start position will be different, but we'll get back to that in a minute. So in our new caches, we append. So while processing a block, I get back another set of cache. So I kind of append that in a new cache, right? So once I've processed all of the blocks, I'm going to go through the layer normalization in my head, the logits, the target, and then I'm going to return the new cache that I've got. So for every time I forward propagate through my model, I'm going to return the new set of caches that I've computed back to the user so that they can build the KV cache from there, right? So I think it's time that we go deep inside the transformer block model. And this is what we've got here. So this is a block where the different components are. First of all, we've got the norm. So if RMS norm is turned on, we're using RMS normalization. Otherwise, we'll just use layer normalization. We have in fact seen the implementation of RMS normalization already. There's no point in repeating it. So from there, we've got LN1, which is the normalized layer of the embeddings, or the normalized output of the embeddings. And again, if RMS norm is turned down, this will result in RMS normalization. Otherwise, we'll go back to layer norm. And then the causal self-attention modern. And then from there, one more round of normalization. And here I'm using the swiglu. So again, if use swiglu is turned on, we will use the swiglu mechanism. And you can see that swiglu is nothing but, again, we've seen this before. X passed through a linear layer, which goes to A, X passed through another linear layer, and then the swish activation applied on it, which goes to B. And then the interaction between A and B is further passed through a third linear layer, and then an optional dropout step. So that's the swiglu activation, if use swiglu is true. Otherwise, we fall back to the previous implementation of the Gaussian error linear unit. All right. So here in the forward propagation, what happens is, and this will be invoked every time we go through one for loop over here, right? So you've got to correlate these things where each block is getting processed, and this call will invoke a call to the forward propagation here. So what is happening here is I get an X, I get the incoming KV cache, and I get the starting position. So from there, what happens is the X is normalized and then sent as an input to the attention mechanism. I pass in the same KV cache. I relay basically the KV cache that I'm getting from above, and then the starting position. And then what I get back is A, the attention output, and the KV cache. So I'm going to do the skip connection thing, where I'm going to do X equal to X plus A, and then I'm going to push X through another normalization, the feed forward, and then do the skip connection thing again. Finally, return the X and the KV cache. So here, now we need to go deeper inside causal self-attention. So this is going to be the meatiest implementation of the lot, because this is where a lot of things have changed. So let's go through it step by step, slowly. So the causal self-attention is getting invoked through the block over here, the attention mechanism, and the input that we are pushing through is the X, the KV cache, and the starting position. So if we see here, the embedding, the number of heads, the dropouts, whether to use rope, which is by default true, the max position, which is again in this case I've taken 4096, the sliding window, attention sync, NKV head, which is nothing but the group size, and these are the inputs, right? So in the initialization step, in this block, many things will look familiar. So I'm asserting the embedding, the global dimension of the D model should be divisible by the number of heads that you choose. And then from there, I'm assigning n head to n head, nkv head to, so again, this is a protective mechanism where if you have passed the group size, then I'm going to incorporate it, or I'm just going to use the n head, which essentially means this will be an implementation of multi-query attention, right? So now what I'm trying to assert is if you have passed a group size, then that in turn has to be divisible by the n heads. So if you go back to the implementation of group query attention, multiple queries will be mapped to one key and value, right? So now for that, if you pass the number of groups, then that has to be divisible by the number of heads you've got. Otherwise, the mapping won't happen. So the group size I'm deriving from here will be the n head divided by the nkv head. So that will be each the size of each group, or the number of query heads each KV group will tend to, right? So that's the number of KV heads we've got. And then D head, as always, will be the quotient of the number of embeddings, or the embedding dimension, now with the number of heads we've got. So that will be the dimensionality of a particular attention head, right? So we just had to put the GQA part in. Apart from this, some of the checks or validations that we have is pretty much the same. Now here, if you see, things have changed slightly. So in the QKV mechanism, what we have been implementing is we used to take thrice the size of a linear layer of an n head and a d head, and then split them post facto after processing it as a single linear layer. But we can't do that anymore because multiple query heads are mapped to one KV group. So what I can't have is Q, K, and V having the same length. So I'll have to process them separately. So what we have here, Q, is just like the implementation before, because we're not doing anything to Q here. So it is going to be the number of heads times the dimensionality of each head. And so Q has its own linear layer unchanged from before. Now the K and V, however, have slightly changed. So instead of the linear layer outputting n head times t head, I'm going to have it output nkv head times t head. So it's going to be only the number of groups that I have configured for. And these are exactly the same. So we could probably have done some optimization here where I do twice this and then split them back. But I've chosen to kind of keep this a little clean, since all of what we're going through is a little more involved already. Then we have the projection layer that goes to n embedding to n embedding, and a dropout. And then we set some properties. So use rope, true or false, rope cache. This is where we are going to pre-compute and store the sign and the cost positions, and then use them to calculate rope. Then the max position. So this again will be used for pre-computing the rope cache. Sliding window and the attention sync, something that we've seen before. All right. So let us discuss the forward propagation of the causal self-attention model. So the incoming X will be split into BTC, and then the first thing that happens is I've literally called this function maybe init rope, because it will depend on whether we are using rope or not, as that's a configuration parameter. We are using rope, so this function will get invoked, and what we're trying to say is If use rope is true and rope cache is none, then I need to build my rope cache, where I'm saying build the rope cache according to the dimensionality of each head. So remember, we'll apply rope on the Q and the K, not the V. So I need the D head, and then the max position, which I've initialized as 4096, and then pass the device, then build the rope cache from here. We'll get into how this is implemented in a minute. I just want to go through the forward propagation. So after the rope is initialized, we've got the QKV, the computation, and this will sort of look familiar. So the view and the transpose is something that we've done before. So we've got self.wq of x, and again, if you remember, wq is the linear layer of the q, and then we make it go through the k, we make it go through the v. So these are the linear layers where now they'll start interacting with each other. Now, if I have use rope turned on, which I have, then I'm going to calculate the positions through a range. This is something similar to the positional embeddings we've already done, right? So if the starting point is 0 and I'm looking at t particular tokens, then I need to arrange from 0 to the number of tokens. So if I have 100 tokens, this will go from 0 to 100, which will result in position 0 to 99. And then from the rope cache, I'm going to get the cos and the sine pre-computed for all the angles and for all these positions from my rope cache. And then I'm going to apply the rope on the Q and on the K. We'll get to implementations in a minute. I just want you to understand the whole flow along with the KV cache and sliding window first, and then we can double click on the rope part. So just imagine this is a black box where we are going to open this up, but right now a single instance of rope is getting applied to the Q and the K, the incoming Q and the K, with the cos and sine that we have pre-computed. All right. So first things first, if the KV cache is not none, then we are going to concatenate the existing KV cache with the current K that I have computed over here. So we've computed the K and the V, and if the KV cache is not none, we are going to further append to our KV cache through the torch.concatenate or torch.cat method here. Now, if the KV cache is none, then I'm going to start and build it. I'll assume this is the starting point. Now, this is where we take it one step further and we go from making it a KV cache to a rolling buffer KV cache. So if the sliding window is not none and KAL size 2 is greater than the sliding window plus the attention sink, so I'm trying to gauge whether I need to evict tokens here or not. So the whole idea of the KV cache is that the KV cache is the dense attention mechanism, but the rolling buffer KV cache is going to be a subset of that, which is the attention sink and the sliding window. So I'm just trying to ensure that the sum of sliding window and the attention sink, if greater than the current length of the KV cache, then I'm going to go in and then I'm going to start evicting the tokens. So the attention sink is a configuration parameter. In this case, I think we have set it to 4. So from the entire KV cache, which I've already built over here, from the entire K cache in this instance, I'm going to only pluck out the first 4 tokens. And again, 4 is the attention sink. And then I'm going to concatenate that with the sliding window that I've configured over here. So I'm going to take the entire batch and then pluck out and go back just as far as my sliding window. In this case, this is going to be 64, right? So I'm going to take the first 4 tokens and the last 64 tokens and then concatenate them together to form my rolling buffer KV cache. So this is the idea of the rolling buffer KV cache. So we went from KV cache over here to rolling buffer KV cache, which is a subset of it. And then from there, I'm now trying to implement the GQA part. So if the NKV head is not equal to N head, then I need to do some things to it. So if they are the same, I'm going to assume I'm doing a multi-query attention, right? So I literally do not need to do anything. Literally, the K of attention and the V of attention becomes the K all and V all, right? But if not, I actually need to repeat interleave. Now, what is repeat interleave? So repeat interleave is an operation that when you specify how many times you want to repeat a particular input, it gets repeated that number of times. So in this case, again, you have to understand that multiple queries are getting tended through by one set of K and V. So for that multiplication to be effective, I need to unpack or broadcast my KV group and replicate them across the number of queries that I have so that I can do the dot product. So I'm going to simply broadcast all of the KV groups that I have to unpack and replicate themselves to the same amount of dimensions as the number of queries, right? So once that is done, finally, I can go through the dot product, the scaled dot product attention, and then from there, take the output, transpose it, contiguous view. We've seen this before. Get it through the projection layer. And again, if the KV cache is not none, I'm going to now construct my new KV cache. Otherwise, the new KV cache becomes the old KV cache. Or rather, the new KV cache becomes the new K and V that I've computed in this step. So I'm starting to build my KV cache. And then I take the K new and the V new and then build a data class out of it. So if we look at the KV cache over here, then you'll see that it's a data class of size. Again, it has a K and a V of size BHTD, right? So this is going to be my implementation of KV cache. The only thing that we have left is the implementation of the rope. So let's go through that. We'll go through two things here. Applying one single instance of rope and then the entire rope cache implementation. So let's get down to it. So first things first, I'm going to assert that the head dim coming in must be divisible by 2 and then set my base, my head dim and my device, and then I'm going to build as per my position. So the position here, I think I've set it as 4096. Now what will happen here is in the build phase, I'm actually building my rope cache. So I've set the max position. Now the rope is actually the inverse, or here literally I'm trying to calculate the thetas, right? And the thetas will be the 10,000 to the power of the position. And this is what it looks like. So torch.arange, we start from 0. We head till the head dimension. And then we take the floats. We convert that to a float divided by the head of dimension. So this calculation is literally going to be as mentioned in the paper for calculating the angles. And then from there, I'm going to take the positions. So torch.arange until the max position. So place where I want to build the cache on. Do an outer. So this literally gives me, if I do this between t and the inverse frequency, for each position, it will give me head dim by 2. So this becomes the matrix. And for each of that matrix, I'm going to take the cos and sine. So this becomes my rope cache. Now, what I'm interested in doing is that if I want to apply rope to a particular tensor, what I'm going to do is, again, my validations aside, I'm going to build my cos and sine so that they match the dimensionality. So I'm going to add 2 more dimensions. X1 becomes the even positions. So this piece literally takes the last dimension and goes from 0 to 4, 6, 8. And then this piece does the odd positions. So it's 1, 3, 5, 7, 9, and so on. And then from there, I'm going to take the x1 part and multiply it with the cosine, x2 part and multiply it with the sine, and then there's a negative sign here. Same calculation goes here, and then I'm going to assign my output matrix back to these values where now the positional information has been embedded. So if I were to correlate this with what we have seen as the implementation of the rope, you will see that it is consistent with the implementation that we are trying to go through. So the m thetas that we have calculated literally are the implementations from the paper itself. We'll go through why the m theta 1 is here positioned as 1 by 10,000 in a minute, but I think that's what the paper says. Yeah, there we go. So this is the general form section of the row former paper, and as you can see, the theta calculation over here has been given by this particular equation that we have calculated. Hope that makes sense. So once you go through this a couple of times yourself, hopefully things will make sense. So we've also gone through the application of how to apply rope once. So which brings back to our causal self-attention model. I think we have gone through all the aspects of it. So we covered RMS norm, Swigglue, KV cache, sliding window attention with attention sync, and rope. So all the aspects are covered. So we can come back to the implementation, and then from there, one last trick that I wanted to show you was I have a generate function that uses the KV cache with all the bells and whistles included, and I have an implementation that does not. So we're going to compare the output once you run it. So in the generate phase, again, my top K top P filtering stays as is. So what will happen here is I'll take the indices, and then for the first time I'm going to seed my entire prompt. So if my KV cache is so I'm checking whether it's the first token or not, or it's the first time that I'm processing or not. If it is so, then I'm going to take the entire context window that was provided to me from the prompt, and then I'm going to process it. But if not, that means I'm generating a new token one by one. So I've already pre-filled my cache with all of the input prompt. All I'm interested in doing is looking at the last token so that I can build my KV cache row by row and save a bunch of computation. So this is where the starting position changes as well. So if this is going to be the first time that we are processing the prompt, then the starting position is going to be 0. Otherwise, the last position of the KV cache will become my starting point. So this is where the start position is not always 0. This is an important part to keep in mind. So from there, we forward propagate it through our model. We get our logits and our new KV cache. And the next logits is going to be the last token. This behavior, we've seen this already. And then the next logits is going to be further filtered by the top P top K implementation. And then I'm going to get the probabilities. And this time I'm trying to keep things more deterministic. So instead of relying on a tiny number manipulating my deterministic outputs, I'm going to directly hard code a greedy output here. So I'm saying if the temperature is 0, then just give me the argmax, else we continue to sample. So from there we go the concatenation of IDX and the next ID, and then we further process. So this is the generate with KV cache. Now without KV cache, the top part remains the same. This also holds true for the first part, but it's also made to hold true for every part. So every time we are going to generate a token, we are going to take, go back to the block size and then process the entire thing, right? So this again, we are manipulating so that it matches the cache path. We're going to get the logits. We're going to get the next set of new logits from there, do the top K filtering, do the probabilities and softmax, argmax for temperature 0, blah, blah, blah. So everything else remains the same except for the fact that from the second token onwards, we here are going to be leveraging KV cache, while we're not going to here. I've written a bunch of tests as well. I leave that as an exercise where I'm just validating the different shapes of the different mechanisms of where I thought I struggled with. So we're going to run our script now. And then we're going to pass the demo. So it goes through a bunch of tests, and you can see that we've both generated, again, this is an untrained model, so the outputs won't make sense. We've generated 200 tokens, and the first time through, we were using the KV cache. So that happens in 0.07 seconds. The second time through, we were not using the KV cache. So that happens in 0.13 seconds, which is almost twice the time, right? So it matters a lot in terms of the speed, and it's a remarkable achievement. So that brings us towards the end of part 3. Now what we have gone through is a bunch of meaty stuff. We started with RMS normalization. We then checked out Swigglue. Then we understood KV cache. Then we understood how it blows up memory and the need to get into grouped query attention. Then from there, the sliding window attention with attention sync. So all of them put together put less pressure on the KV cache, thereby blowing up the memory lesser and lesser, which led to rolling buffer KV cache. And then finally, we went from transformers being positionally invariant to introducing absolute positional embeddings, to them not having the relative embeddings. So we introduced relative positional embeddings, and then from there finally rotary positional embeddings, which combines the best of both worlds concerning absolute positional embedding, their freedom to cache and operate independently, and the relative part, which also is embedded in rope. So all of that put together, we constructed an elaborate attention mechanism along with KV cache, sliding window, everything. So hopefully things are starting to make sense now. All of the code is already available in the GitHub. I strongly encourage you to follow along, or maybe try and build your own based on the explanation and your understanding. Hope you had a lot of fun learning this part. Thank you very much. Hi, hello and welcome to part 4 of the LLM from Scratch series. And in this part, we're going to cover various aspects of training the modern architecture that we've just gone through. So we'll start from switching to byte level to byte pair encoding tokenization. We'll go learn gradient accumulation and mixed precision. AMP is something that we've covered already. We'll go through gradient accumulation and the implementation of it. We'll look at learning rate schedules and warm-up. We'll look at checkpointing and resuming. And we'll also look at, in details, TensorBoard logging with an option to switch to weights and biases as well. But weights and biases will be out of scope for this. So as always, we start with our orchestrator.py and the layout in front of you. And all you need to run this demo is run Python orchestrator and pass a demo argument. Then from there, what happens is the tests run and the train and sample.py run. We probably won't be covering sample.py because it will be self-explanatory, especially after covering the previous parts. We'll hyper-focus on train.py because I want to just unpack some of the aspects of how a production-grade training actually happens. So we'll jump to train.py, and here we've got our arguments. So we've got the data argument, the out directory argument, we'll be using byte pair encoding with the vocab size, block size, the number of layers, the number of heads, the number of embeddings, dropouts, everything all too familiar. This time, there will be some training parameters in addition to what we have seen before. So batch size, epochs, steps, the learning rate, the warm-up steps, whether to use mixed precision, and how many steps to accumulate, the gradient accumulation part. Then there'll be a logging step, whether to use TensorBoard, which will be by default, and then how many steps do you want to save your checkpoints, and how many checkpoints do you want to keep. We have the device, and then we have from the out directory, we're grabbing and checking if a checkpoint exists. So this script has the ability to resume training if you choose to do so. So if I have a checkpoint present, the checkpoints will get loaded. Otherwise, training will start from scratch. So we start from the checkpoint, and then we load the particular checkpoint if it exists. And if it does not have a config, we will error out. So in order to not guess some of the parameters, adjoining parameters in the model, apart from the weights, like the vocab size, the n layer, the n head, the n embedding, etc., it's mandatory that we save our model not only with the weights, but also with the state dictionary of all of the configurations. So we're looking for our tokenizer in this tokenizer_dir.txt. And then once we find our tokenizer, we are simply going to load it, and that will take us to our saved tokenizer directory. So we come to the part of the tokenizer now. We initialize our tokenizers and our tokenizer directory. And if we have the checkpoint, which simply says if it exists or not, if the checkpoint path exists or not, then we'll load the BPE tokenizer, and then we'll load the saved tokenizer directory from this. From there, we assign a couple of variables from there. And if it does not have a checkpoint, it loads a BPE tokenizer and then trains it based on the data path that you've passed in the argument. And then it creates a tokenizer directory. It creates the directories if they don't exist already, and then it saves our trained tokenizer. So here, what is going on is, if you have a byte pair encoding tokenizer, it works on the data parameter that you pass. Please note that this is the same data that we're going to use to train our LLM as well. Usually these are different. So you want to use a different data set for a tokenizer because you want to include more aspects of language, more aspects of nuances like programming languages, trying to capture indentations and different nuances in syntax. So your data typically for the tokenizer, for training the tokenizer, will be different. Now, while we do call this training the tokenizer, there is no training in the machine learning's conventional aspect. So all we are doing is collecting statistics and merging them together. So Wikipedia has an excellent example on the byte pair encoding and how it works. So we start with a stream of strings here, a stream of characters here as an example. Now, since the most frequently occurring pair is AA, we replace AA by the term Z. So right now, if you look at this stream of characters, our vocabulary size will be the letter A, B, C, and D. But now if we are deciding to merge Z to represent, or merge AA to be represented as Z, our vocab size increases from 4 to 5, but we need lesser number of tokens to represent our stream of characters. And then we continue on this journey to take pairs, and we can set cutoffs based on what should be the minimum frequency I should be able to see a pair before I decide to merge them. And all of that put together iteratively, we can have a stopping point where I can hit my frequency threshold, where I should be able to see a particular pair of characters at least a certain number of times, or I've hit my vocabulary size limit. So in this case, we will be using 8,000 as our vocab size. The number of bytes that are present in the UTF-8 in the byte tokenizer will be 256. So we will see 256 bytes getting progressively merged to form an 8,000 vocabulary size byte pair encoding tokenizer. So we come back to our byte pair encoding tokenizer and follow the implementation. So this is our byte pair encoding tokenizer, and this is how it is implemented. Now, for a change, we will be importing a library and not be implementing our own byte level BPE tokenizer. There are two reasons for this. One, there's no actual gradient descent and backpropagation happening. So implementing this would derail our focus from getting into the actual aspect, the BT aspect of training a model. Second, the tokenizer's implementation has been done in Rust, so it's incredibly fast, and I highly recommend that this should be used in a production environment. And if you do want to double click on this topic further, Andre Karpathy has an excellent material, has an excellent video on how it actually works, where he builds one from scratch. So with that, we are going to initialize our BPE tokenizer. So we're saying if our BPE tokenizer is none, then we need to install our tokenizers. We set the vocab size. We're going to set some special tokens. So this will be the BOS and the EOS token, the beginning of sequence and the end of sequence token, the padding token, so that if we pass a batch and the batch should be of same length, then we can use this token to pad it, any unknown token, or if any token we want to mask explicitly. So the training starts over here. This is what it does. All it requires is a data path. Now we determine whether the data path is a directory or just a file. If it is just a file, then we're going to wrap it in a list. And then if it is a directory, we're going to pluck out all of the txt file, whether nested or not, from this particular folder and make a list of txt files here and use that for our training. So all we need to do here is tokenizer.train, pass the vocabulary size, the minimum frequency, and the special tokens. And this will ensure that our tokenizer is trained. So once we train our tokenizer, we would actually be able to view some of the aspects of the tokenizer, and this will be way more clear once we run it. But since I've run it already, I'll just show you some of the output. So here is our vocabulary.json. Try and format it. And we see that we've only got about 7,600 tokens. This is because we might have hit our stopping point with respect to the minimum frequency of the occurrence of a pair. So if I scroll right to the top, the special tokens come in first, and then all of our UTF-8 tokens come in. So the first 256 plus the special tokens would be dedicated to single characters only. And then from there, as I scroll through, you can see that merges and patterns have started emerging. My best guess is this particular character stands for a space. So space should gets a token ID of 754 and so on. If we want perspective on what all has been merged, and this again will be data dependent on what data you provide to it. We've provided a tiny English text full of poems, right? So it'll take a look at this, and it will be leaning towards collapsing a lot of these multiple spaces. So this can be set towards Python code as well. If you just provide a lot of Python code, all of the indentation will start appearing as a single token. What you can also do is check out merges.txt, which I've written. So here it talks about all of the pairs that got merged. So here we can clearly see a space and a space got merged to create a double space. Further, a double space and a double space also got merged. And then from there, different characters started getting merged. And then as we scroll through, we will see that characters of more than one length are starting to come together over here. So H, A, D, A, I, R, A, S, E, and so on. I've seen a couple of these before where it starts to catch nice suffixes. So for example, CTION was a particular token that got merged. So as you can see, there are 7 occurrences of the term CTION: affliction, actions, ruction, correction, right? So you can easily look at a tokenizer as something that do not mean words. So they're not a replacement for words. They're just smart statistics so that we can optimize our LLM to use as less tokenizers as tokens as possible, more effective. So we train our tokenizer and then we save our tokenizer. So this is the implementation of the save module, where I'm simply taking the folder structure given to me and then saving the different aspects of the tokenizer. So there's nothing really to explain over here, so we'll move on. Now, if I don't encounter a BP tokenizer, then I'll finally fall back to my byte level tokenizer. From there, I'll ready my data for the training. So I'll make a loader over here where I'm passing my data. This again is the same data that we use for tokenization, which is usually not the case. So if I go towards making a loader, then we'll look at a text PPE buffer that is getting created, which is defined over here. So what we are doing is reading the entire text file again in memory, since this is a tiny file. In a production grade setting, again, you will deal with a much larger data set, and you would probably load this iteratively in batches and create a data loader out of it. So in this case, we load the entire text in memory and then create or encode the entire text like so with our tokenizer. So this time we'll be using our BPE tokenizer. We'll encode with our tokenizer that we have trained. We have a couple of implementations of the length and get item as well. These should be things that we have seen before. So with the length, I want to specify that I want to return the max of 0 and the number of elements that this particular sequence has minus the block size, so that if I pick a random integer and try to create a batch out of it by adding the block size, then I'm still protected and I don't spill over my sequence of tokens. From there I have x. So this will be a random integer that will be passed, where I'll take that integer till the context window and then right shift it to get my y and then simply return x and y. So we've got our data loader over here, and then we return a data loader, which is again, this will be a lazy load implementation. So as and when we iterate through a data loader, it will at runtime ask for each batch one by one. So we get back to our data loader, which is again a lazy loader. This won't store the entire data in memory. Then we get to our build model config. So here what we are trying to do is that if we find a checkpoint that has the config element present in it and the vocabulary size of the model is equal to the vocabulary size of the tokenizer, then all is good. If it is not, we're going to raise an error. And here, if I don't have a checkpoint, I'm going to create the model configuration from scratch based on all of my arguments. So the n embeddings, the n block, the layers, etc., etc. Whether to use swig loop or not, rope or not, usual bells and whistles that we have seen in the previous part. So we're going to build our config from there. So taking a look at this here, it simply returns all of the desired configurations that we are well aware of and have seen this before. Now this section, we do a bunch of declarations. So this should be an all too familiar model initialization. So we're not going to go into the aspects of what a GPT model is constructed with, because we've already taken care of that in the previous part. We have an optimizer, and we've used this optimizer before with similar parameters. So this should also be pretty familiar. total steps we're taking as the minimum of the steps parameter passed, or the epochs times the length of the train data loader. With warm-up, we want to do the minimum of the warm-up steps or the total number of steps divided by 1. Now we've got a scheduler over here, warm-up, cosine LR, and we pass in our optimizer, the warm-up steps, the total steps, and the base learning rate. Let's double click and find out what is going on over here. So this is our warm-up cosine LR implementation. So what we have here is, in the initialization phase, we assign the optimizer, the warm-up steps, the total steps, and the base LR. And in the step phase, I've got two aspects to it, or two conditions. In condition 1, I am in the warm-up stage. So this specifies that the current step is less than the total number of warm-up steps that I have configured so far. So what this will do is linearly increase our learning rate. We'll check this out in a minute. If not, then we fall back to our cosine scheduler. So if you look at this, the base learning rate has been selected as, I think, 3e minus 4. So let's pull up a terminal and check out what happens. So we've got our base learning rate. So if I pull out a quick Python shell, so we've got our base learning rate, which can be assumed to be something like this, 3 minus 4. And then at the first stage, I'll be multiplying with my step number divided by the total warm-up steps. Let's assume that to be 20. So if I do this, I get a tiny number as the learning rate. Now, as the warm-up steps increase, the learning rate increases gradually. And then eventually what will happen is, as the warm-up steps are complete, we will approach towards this being the actual base learning rate that we had set originally. The core idea of this is you want to take the guesswork out of the base learning rate as much as possible. So what you want to start with is not directly with the base learning rate, but you also want to settle your model into that base learning rate by starting with a much tinier learning rate and then working your way up on a linear schedule. Now, once you reach your base learning rate, you're actually going to do the reverse. So we're going to progressively, in a cosine schedule, step down our learning rate so that our training is stable. So that's our warm-up cosine learning rate scheduler. Now here we've got automatic mix precision combined with the gradient scaler combined with the gradient accumulation steps implementation. So what is gradient accumulation steps? Now, typically you want a higher batch size so that your model could converge faster, but then you're restricted by the number of GPUs and the memory it has. And that's why what happens is, if you set a batch size of 128 and the entire batch cannot forward propagate and back propagate in one shot, you can set gradient accumulation steps to be, let's say, 4. So what will happen is the data will forward propagate and keep adding the gradients in mini batches of 4. So let's say row 1 forward propagates and I compute the gradients. The next sequence comes in. The next sequence's gradients will get added to the previous gradients. So it gets added progressively. So by the time you get to the 4th mini batch, you've accumulated your gradients additively, and then you back propagate in one shot. In that way, you can use a higher batch size. So if we look at this implementation, we've got an initializer with the optimizer and the gradient accumulation default to 1. We'll probably pass 2 or 4 over here, whether or not to use automatic mix precision. Our scaler, and this is something that we have seen before in the previous parts, how to use or what the gradient scaler does. And then from there, since we are accumulating a mini batch of gradients, the loss gets added over time. So it should be actually divided by the number of accumulation steps that you have, and then it should be back propagated. Now, this is an important function, should step. So the idea is PyTorch has a dot step function which actually does the back propagation, without which you will only keep accumulating gradients. So in that case, what happens is you should avoid calling the step function in PyTorch during the training phase for as long as you have your accumulation steps. So here I'm trying to specify whether the PyTorch step should be invoked or not. And we will be using this particular function in our training step. We will check this out. And then the actual step where we're stepping through the optimizer, doing the actual back propagation and updating the weights and the parameters of the model. And if we have AMP enabled, then we do it via the scaler, where it scales up the loss in order to avoid gradient underflow. So we come back to our train.py. That's our AMP grad implementation. And then from here, if we have a checkpoint, or if our model stopped training in the middle because it encountered some error or we decided to stop it, we can load the checkpoint and then resume from there. This is the logging part. So here I'm initializing the logger. So here arguments.log defaults to TensorBoard. And if it is TensorBoard, I've got a TB logger class, which is defined up top. And here I'm going to name my run as a particular prefix concatenated with the timestamp. And then I'm going to determine the directory for it. And then this is where the summary writer comes in and will be available for me to write my logs. Now I will also be writing histograms. So I'm capping or upper capping the maximum number of elements not to blow up my TensorBoard. And then there'll be this run directory. So the log function will be a pretty busy function that will get invoked from various aspects of the training. I think it's best to check this out when we actually watch the training happen. And there are some other aspects to it. We're going to log the histogram of some of the weights like the QKV and watch their stability. We're going to log some text as well so that we can sample our LLM across every few steps just to check how the quality of the generation is improving. And then I've got a bunch of placeholders for hyperparameters and stuff as well. The weights and biases implementation, on the other hand, is extremely minimal and is left as an exercise. So we come back to train.py. We've initialized our TensorBoard logger and we are logging our hyperparameters to TensorBoard through passing our logger, the arguments which contain the hyperparameters. So this will be the batch size, the n layer, all of it, and the total number of steps. So if we look at this particular implementation, then if it is not TensorBoard, then we want to return because we don't have any other implementation for this apart from TensorBoard. Then we create a dictionary of all of the hyperparameters that we know of. So the vocab size would be coming from our arguments.vocab size and so on. And then all we need to do is logger.hparams, meta total steps will be different. So this dictionary will contain all of our hyperparameters of our model, and this will contain all of the total number of steps for which we have trained. So from there, we can come back to our train.py. Now here, if again TensorBoard logger is enabled, what I'm doing is taking a random batch of data from the train loader. So this will give me one batch of data, X and Y, and then log it. So just as an initial, just to see that what is the quality of generation before training our model. So we've got the logger, the model, the XB and the YB. And then we're going to log that particular graph wrapped with the tensor only version of the model, which essentially means that here I've got a very quick initialization of the model in question. We put it in eval mode, and then we forward propagate. And then if out is an instance of list or tuple, for every token that we have generated over here, we return it. Right, so got a nice clean wrapper over here. And that's a logging bit. Again, we'll go through the different logging aspects once we get to it. This block is coming from real world pain. So what will happen more often than not is if you're going for overnight training, the whole process seems to die on you more than once actually. So what this will do is every time your process is about to die, let's say you're running a program on your terminal and you press Ctrl+C and it says keyboard interrupted, and then the program dies, right? So what happens behind the scenes is actually a sig term or a signal to terminate is sent to this particular program, and it turns out you can actually handle that request. So in this case, what I'm saying is, if I get such a Ctrl+C request or a termination request, I'm going to run my on_term function, which will turn on a flag, which when turned on will actually save a checkpoint in our while loop. So if you see this, while our model is training, I'm checking at every iteration whether the save requested flag is true or not. And if it is, then I'm actually saving a checkpoint over here. So that's what this thing does. All right, so let's go through the training loop. So we set the model to train, and then while the current step is less than the total number of steps that I have configured, I'm going to invoke an iteration of our data. So xb and yb, a batch of x and a batch of y. If the current step exceeds the total number of steps, then we're going to break. If the save requested flag is true, we're going to go for an atomic save all. We'll look into this function in a minute. I'm noting the time over here because I also want to log my throughput or the tokens per second. So at this point, I'm taking a snapshot of the time. I'm transferring my data to my device. Now with AMP enabled, I do a forward propagation, and then I do an AMP based backward. So this will simply invoke our AMP grads backward function, which we have already seen before here. So based on whether we are doing an AMP based training or not, we'll invoke the scaler or simply do a backward prop. So here we get to invoke our should step function. This is where we actually check whether the current step is a multiple of the gradient accumulation step or not. So now if we relook at that function, then we're checking that this particular step, is it completely divisible by the accumulation step? And if it is, we will actually do a step. So we'll actually do a scheduler.step if this is enabled, and then increment our step. Now we've also got to save every parameter. So let's say if this is configured to 50, we'll just save a checkpoint every 50 steps. So atomic save all, we pass in the model, the optimization or the optimizer, the scheduler, AMP object, the step, the current step, the out directory, the token directory, and the keep last k. What it does is it actually, so since we are saving every 50 steps, and let's say you're going to train 500 steps, you don't want to blow out your disk memory by actually having a bunch of these intermediate files saved. So we have configured keep last k as 2, so it will only maintain a rolling buffer of the last 2 set of weights, and then the config build that we have seen before that contains all of my hyperparameters. So again, with the TensorBoard logger, we're going to do a checkpoint. And now let's look at the implementation of atomic save all. So with all of the input that we have seen, we're simply going to save a checkpoint with the model, the optimizer, the scheduler, the AMP, and all of the details here. So that's how the PT will be written, or the PyTorch file will be written. So we get the last checkpoint from this particular function. So from our out directory, we'll get the last checkpoint, and then we'll also just return a hard-coded model underscore last, and then we'll rename the last step to the model underscore last, so that we know that this is the last checkpoint. And then from there, this is the implementation of the keep last k. So we're sorting our directories with all of the PT files that we have, and anything that is not within the scope of the keep last k will just be evicted. So this is a way to delete these files. We'll see this in action once we train our model. So that's our atomic save all. Now in the logging step, we have every 50 steps, we're going to do logger.log, the step, the loss, the learning rate. And then we're also logging a bunch of these runtimes. So this will be the throughput or the tokens per second that I want to measure. So if I take a look at log runtime, I'm also taking a date snapshot and then subtracting the previous timestamp that I got from here. Now within this time period, a total of XP number of tokens were processed. So I can calculate the tokens per second. And then if you're using a GPU, you can go for the amount of memory that was allocated by CUDA. And then I'm logging all of the metrics here. So we'll come back, and now we're looking at model stats. So with model stats, what we are doing here is, first of all, we get the parameters of the model, and then we take an L2 normalize or L2 normalization of the entire set of parameters of the model, and just to track it over time and see that how they have increased or decreased. So this will be interesting to look at. Goes to show how much stability our parameters are undergoing. We'll do the same thing for gradients. Now we are doing a lot of processing with respect to the grad scaler as well. So this will be an interesting metric to track as well. Now we're doing a torch.norm on the gradients as well. So we're logging both of them here. And if I have histograms enabled, I will also have histograms of the gradients and parameters. So here we are not doing the histograms of the gradients and parameters, but we'll do it for the QKV. Now here I've got a maybe log attention function where again I'm passing the logger, the data, so that I can recompute some of the attention mechanisms and pluck out some intermediary variables. So this is our implementation of the maybe log attention. So here we are actually getting a batch of the input data, and this we are doing is just because we are importing our model from the previous part, and we'll have to just run it again so that we can intervene in the middle and hack into or hook into a bunch of these intermediary outputs. So we've just decided to run one forward propagation again to get the particular tensors for the QKV. So we've got X, it goes through the token embedding, and then for every block, it goes through the QKV, and then finally the logging of the histogram and the logging of the L2 mean of all of these QKVs happens over here. So once we see this, things will be clear. And then I've got a very cheap implementation or an approximation of the FFN, so that we can approximate that how after the first block the token comes back to the second block to be processed. And then finally the log samples is simply every few steps we are going to literally generate samples and log some of that text so that we can view it. Atomic save all is something that we've seen before. So we're doing the final atomic save all so that our model final checkpoint of the model can be saved, and that should do it. So without further ado, let's actually run a training step and see things in action. So we'll exit our Python shell and come to part 4. Now you see that I've already got some data from previous runs, so it's better that we remove all of them and then start from scratch. So this is going to be our implementation, runs a bunch of tests as usual, and here I've got a runs folder and a tokenizer, and you'll see that the model.last is always a last snapshot of a particular step, and then every 50 steps the model is getting rolled over so that we are not storing more than 2 instances of our model. So once the 250 comes in, the 150 got evicted. Once the 300 comes in, the 200 will be evicted, like so. So that goes for a nice implementation. And once we've completed our model training, the checkpoints will be saved. We're going through just to generate stuff as well. And in our orchestrator.py, we've got the command to run our TensorBoard. So let's check that out. So we've got our log directory as runs/part4demo. So we've got our TensorBoard running. First things first, I would like to look at my hyperparameters. So with the batch size, the block size, the dropout, epochs, gradient accumulation, and the total steps is something that we have logged. Now if we come to the time series, we will be able to see the loss decrease over time, so that's good. With the cosine decay, after the warm-up, we are seeing that it's gradually decreasing over time as per our cosine schedule. We've got our total number of steps as 300. We've got the different QKV histograms and their L2 means. We'll look at histograms separately. So here we'll be able to gauge whether they're able to follow a normal distribution and are being stable or not. So you'll be able to see that for the block 0, the K histogram, it started off with a much wider band in the 100 step, but by the time it got to the 300 step, it's much more narrower. That means the variance has reduced, which is exactly what you're looking for in a training run. Similar things are happening for Q, K, and the different blocks that we've got there. In the system metrics, we've got the GPU memory allocated and the throughput tokens per second. So that's all good. And in our training, we've got the global L2 normalized version of the gradients and the L2 normalized global version of the parameters. And also notice that these have decreased over time, which means lesser the variance, the more stable the training, the more smoother the convergence. So we've got our scalars over here, nice clean view to look at. We've got our distributions, and this is what I'm more interested in, the histograms, where the QKV blocks have been logged over here, and at every step we can see that the variance is reduced. So this is good. Now in the text, I want to show you how at every logical number of steps, we are actually logging what the model is outputting. So at step 50, this was the quality of the generation. And you can see that by the time we get to 300, the quality would have kind of sort of increased a little, right? So more training, more stability, better generation. So that's all there is to it on the TensorBoard logs. Now, I want to show you a couple of test cases just to play around and show you some of the capabilities that we have built. So I'm going to remove all of my checkpoints once again. And what I'm interested in simulating now is actually some of the painful aspects or the negative testing aspects of our venture. So what we'll do is we'll start training, and by the time we see a couple of checkpoints, we will actually press Ctrl+C to stop the training and observe the behavior. So always we run our tests and our runs have started. So we have the first checkpoint come in. We'll see them rotate a couple of times. So we have the 100 checkpoint, and let's say let the next checkpoint come in, and now I stop the training by pressing Ctrl C. So I've had a keyboard interrupt, and you'll see that when I was about to stop the training, it was trying to process its 180th step. And because of our sick term implementation, we will not fall back to our 150th step. We can actually have the step during which our training failed. That's powerful. So it saves a bunch of computation. So now I run this thing once again, I'll get a notification that it has detected that it has been trained for 180 steps, and it will just resume from that. So let's watch that in action. So buried beneath the bunch of logs, we've got this. So it is resuming at 180, and you will see that the rollover is happening now, where we've gone from evicting the 150 and the 180 to the 200 to now we have completed the training entirely. So this is good. So some of the capabilities that we have developed in this, combined with the modern architecture that we have seen in the past, would actually become some of the, or will take you close to some of the production grade implementations that you will do for training large language models. Hopefully this part was helpful as well, and you got exposed to some of the training aspects that are less discussed, I would say. Some of the model architectures are more discussed, but babysitting the training process is also a lot of pain. Hopefully you learned something and had fun while doing it. Thanks a lot. Hello and welcome to part 5 of the LLM from Scratch series. In this part, we are going to cover mixture of experts. Now, we've spent some time over the last 2 parts modernizing the architecture, as well as going through how a production grade training might work. In this, we are going to concentrate on one more piece of modernization of the core LLM architecture from the vanilla transformers. So we've taken care of modernizing the attention block. This time we're going to focus on the feed forward network that happens outside the attention block, but within the transformer block. So we're going to cover some theory on expert routing, gating networks, and load balancing. We'll jump to the implementation, and then from there, we'll try to watch a worked out example to figure out how it all comes together. So first things first, what is mixture of expert? Now here we have a rough diagram of the architecture of mixture of experts. Now, as you can see, all of the attention blocks have been collapsed in. So this can be thought of as the more modern version of multi-headed attention, with the group query attention and the swig and the rope and all the bells and whistles that we have discussed so far. But from there, instead of feed forward network, what happens is there's a gating function over here, or a router, which takes the output from the attention module and then decides to route it to one of these or one or more of these experts. So this router will have probabilities emitting from it, and based on that, we are going to route it to one or more of these experts. Each of these experts is a multi-layer perceptron or simply a linear layer, and then from there, the whole thing goes forward. What's the point of doing this? Now, first of all, it out of the box gives you more parameters. So the more the parameters, the expectation is that the more sophisticated the model will be. But instead of a dense implementation where every token and its parameters propagate through every MLP that you have got configured over here, we have a more sparse implementation, and this sparsity ensures that during inference, only a fraction of these weights are activated, thereby giving you more throughput with more parameters. So even though you can have a similar model with a dense parameter, it's more beneficial to have an MOE setup. This is because less number of activations means lesser computations, means more speed. So during training time, the model fine-tunes itself to pick the right combination of experts. So you can think of it intuitively as one can be the coding expert, one can be the language expert, and so on. The part where this particular expert tends to certain tokens is not within ourselves. It will be within the learning process. And then from there, the whole thing propagates and we have more layers of this stacked together. So it'll look like the model will have a lot of parameters, but only a fraction of them will be activated during inference time. So that's the intuition or the inspiration behind learning mixture of experts. So we'll jump right down to the implementation part with that short introduction. So we've got the orchestrator.py, and along with it, we'll look at all of the mixture of experts components that will lead up to a hybrid architecture, which can be a combination of a dense and a mixture of experts module. So I've got my unit tests here and a demo moe.py. We are not going to train a model here. We aren't even going to come up with the entire LLM. We're just going to pluck out the MLP piece and then double click on it, zoom in on it, and then just use the inputs and outputs for that particular module. Now, since we've already seen the entire architecture evolve a lot over part 3 and part 4, there's no point in cluttering by building on top of it further. It just goes for a cleaner way to understand what mixture of experts are. If we just pick it apart and understand it, putting it together is the trivial part. So we've got the demo MOE over here. Now here we have some of the arguments that are passed to it is number of tokens we want to generate, number of hidden neurons you want to have within your MLP or the linear layer, the total number of experts, and out of that you only want to pick the top K experts, CPU implementation, and then the device. Now here I'm simulating a batch of sequence of tokens coming in. So if you have configured 64 tokens to come in, I'm actually splitting them over 2 batches so that we can simulate what happens in a batch forward propagation. Now here is our MOE architecture. Now once we invoke that, we're going to forward propagate it, and I've just got some helper code here that will help us visualize the shapes, but this is where the entire architecture is hidden. So it takes as input the number of hidden neurons you want to process and the number of experts along with the top experts you want to pick for processing a certain token. So in this case, we are using top K as 1. I think we will override that by 2. Okay, in this case, we've got top K as 1 and we've got a total of 4 experts and we're trying to process 6 tokens with, for the MLP, the hidden neurons will be 128. So here we've got the MOE implementation where a mixture of experts layer has been implemented here. Now, there are many implementations available. We are following what is present in this particular paper. So we're going to follow the switch transformers paper over here, which was one of the more original implementations of the mixture of experts module. So we come back and we watch the initialization. So the dim parameter is nothing but the D model or the number of dimensions that will go in to this particular layer. And then we have the total number of experts, the top K experts, the top K gate. This is going to be our router or the gating function. And then we'll have a module list of all of the experts. So as per the number of experts, we are creating a module list of the expert MLPs that we're going to configure. So we've got the dimensionality input going in, and the multiplying factor is going to be how much more hidden neurons we want against each piece of input. So we've configured this as 4. So that means a 128 embedding coming in will have 128 times 4 number of hidden parameters in the MLP. So we're using Swiglu and drop out if necessary. I think this is turned off. So let's look at the top K gate. So here we have the meat of what is going on in the mixture of experts module, which is the routing or the gating function. So first of all, we assert whether the top K picked has to be at least greater than equal to 1 and has to be less than the number of experts. Then we assign the number of experts and the K and our WG to be a linear layer that takes in the input and then outputs the number of experts. So this is going to be a simple linear layer, the gating function, and we'll treat the output neurons as the probabilities of moving towards each expert. So we've only got top k as 1. So this will emit 4 pieces of probabilities. And then from there, we're going to pick the top one. So once you propagate the input through this linear layer, you're going to get the logits, and then you're going to get the probabilities via the softmax. And then once you have the probabilities of those 4 experts, you're going to pick torch.topk as per your configured k, and then you will get the top k vals and their indices. So here, what we're doing is splitting the probabilities by size 0 and size 1. So one important thing to notice is that we are actually going to pass our batch of tokens as a single dimension. So it's usually split by the batch, the tokens, and the channels. So here it's going to be tokens, which is going to be a product or the squeezed dimensionality of the batch and the sequence in each row. So with that, we'll get 2 sets of probabilities by forward propagating it through our data. Now, we're going to calculate the importance, which is going to be the mean of all of the probabilities along the expert dimensions. We'll watch this all in a minute when we run this. I think things will be clearer by then. So here what we're interested in is calculating something called the auxiliary loss, which says that this is going to be another loss component in my LLM, which penalizes my architecture if it skews towards an expert. So when you go and implement a mixture of experts architecture, what happens is it gets prone to what is called the celebrity problem, or all of the tokens start getting concentrated on a very few number of experts, so that the expertise is not diffused well over the model. So for that, what we need to come up with is an actual loss function that penalizes for imbalanced routing. So we'll again watch all of this and follow this through an example in a minute. So we're going to take the fraction of tokens assigned as primary. So we're taking the first dimension over here. We're going to calculate load, and then load is going to be again the dispersion or the diffusion of the tokens through the different experts. And this is the formula for the auxiliary loss. It's the importance times the load for each expert summed up multiplied by the number of experts. Now, since we've got this print function, I'll probably comment out before pushing this, so you'll probably need to turn it back on. This will give us a lot of visibility into the probabilities, the importance, the hard one, load, and auxiliary loss. And then finally, we return our top indices, top k vals, and the auxiliary loss back. So once we are back, we have a module list of expert MLPs. So let's study that. Now the expert MLP here is pretty simple. So if I have Swiggloo turned on, these are going to be my different components. There's a linear layer, there's another linear layer, there's a silo activation or a sigmoid linear unit activation, and then there's going to be another linear layer for the out and a dropout. And since we've seen this before, that the input X will go through input 1 set of weights, it will also go through input 2 set of weights and activation, and then A and B will be multiplied together and pass through another out linear layer, which will then go through the dropout. So this is going to be the implementation of our feed forward layer. So you see, this is just one MLP layer. We will have 4 of them, since we have 4 total experts. So we'll have 4 of them assigned as experts. Right, so what happens in the forward propagation? We receive a batch of data, and then we squeeze down the batch and the sequence dimensionality into 1, and then we flatten it out. Now, once we flatten it out, we propagate it through our gating function, and we get the indices, the weights, and the auxiliary loss. Now from there, in order to calculate my Y, I need to iterate through every expert and find my slot for the top K expert, make sure whether I'm looking at the top expert or not. And for that, I'm going to select all of the activations from the output of my gating function and then pluck out and impose that on top of the zeros that I've configured here. I know I'm going a little bit faster with this, but I really want to get to the example part where we can actually visualize a lot of these propagations, and that will make it a lot of self-explanatory instead of explaining or dry running line by line through theory. So finally, we change our y to the BTC dimension and return our y along with the auxiliary loss. So at this stage, what can be done here is with the auxiliary loss, when it goes down the workflow, we should actually add this auxiliary loss as part of the overall cross entropy loss that we have and then back propagate from there. So that is going to be our implementation. And then once we run this, we will finally go through the hybrid function, which is again going to be a pretty easy implementation once you start understanding it. So without further ado, we'll run our solution. So we're going through orchestrator.py, which runs the tests and prints a bunch of stuff, and we have the output ready. So we started off with 6 tokens, and we have 4 experts with the top K as 1 expert. So this is the first tensor that we see, which is actually the probabilities. So what is happening here is we have each row represented as a token. So we have, since we are processing 6 tokens over 2 batches, all of them have been concatenated and squeezed out into one single dimensions. So if you have 3 tokens per batch, you will actually see 6 tokens here, which is what we've implemented. So if I were to go back and confirm that, you will see that I'm taking my random input and dividing it by 2 to simulate 2 batches. So although I'm processing 6 tokens, I'm representing them as 2 batches of 3 tokens each. And then when I get to the MOE function, before passing it to the gate, I'm actually flattening out my input like so. So I get a BTC dimension tensor, but I'm reshaping them to S cross C so that the batches and the tokens can be one stream, and I get to know which expert to pass through. So you see here that this is a 6 by 4 matrix. So each row represents a token and each column represents an expert. So if I were to pick apart this cell, then the way you interpret it is that 0.1651 is the probability with which you should route token 1 to expert 0, right? So if I pick a random cell over here, then this represents the probability that the token 2 should be routed to expert 2, or the third expert in this case, out of the 4 that we have, right? So now this is how the probability map looks like. Now, if we move further down the line on how the gating function is behaving, then from the probabilities, we are actually calculating importances. So this importance basically means how much tendency that a particular expert has to process a token, right? So it's a simple calculation. So we're going to take the mean of the probabilities along the 0th dimension. So if I look at all of the importances printed out, I will see that it is a tensor of 4. It's a vector of 4 elements representing each expert. So this is the propensity for a particular expert to process a token. It's simply the probability. It's simply the mean of the probabilities. So if we hand calculate this very quickly, so we've got 0.1651 times 2337 plus 1776 3395 2751 and 2857 or 07. the whole thing divided by 6, and we get our probabilities as 0.24528333 for the first expert. So this has been approximated to 2453. So this is the propensity or the probability with which an expert will process a token, or expert 1 will process a token. And you can see that it's pretty diffused by the state of things. And then the hard one is actually getting picked as, now even if you have top K configured as 2, doesn't matter. What we are interested in grabbing here is the fraction of tokens assigned as primary. So for this token, if I see the different probabilities, I can see that this is the highest probability. So with top K as 1, this expert will be hard assigned this particular token. So that's why this tensor shows 2, which is the index of the third expert. So 0, 1, 2. So this is the highest probability. Now if I look at the second token, I can visually see that this has the highest probability. So the number here should be 1. In the third as well, this has the highest probability. So 1 comes up again, and so on. So I've actually got the index of the expert which became the primary processor of a particular token. That's what I've got with hard ones. So we've figured out what the hard ones do over here. And then from there, we need to understand what the load is. So it's pretty simple. I take the number of tokens processed by that expert and then divide it by the total number of tokens. I'll repeat that. So I'll take the number of tokens processed by that expert and then just divide it by the total number of tokens. So in this case, if I were to pick apart expert 0, then I can see that it has processed only 1 token. So 1 divided by 6 is what I'm going to assign as my load for the first expert. We'll quickly check that up, and the math adds up. Now in this case, for the second expert, however, we've got 2 tokens processed by the second expert. So this should be 2 by 6, that is 1/3, which is 0.33. Now the same goes for the third expert, or the expert at index 2 as well. So that's why its weight is 0.333. And for the last one, we've only processed 1 token. So the load on this particular expert is this, right? So we've got the different importances of an expert, and we've also got the different loads on the different experts. So all we need to do is plug in with this formula. So E times importance times load sum, and then whatever that comes out to be. So in this case, the auxiliary loss comes out to be 1.0034. So in order to really nail this out, right? So what we might need to do here is, let's take in a Python shell and try processing it from here. So here I've got, let's say, the load is going to be absolutely diffused. So the load is going to be absolutely diffused, which means every expert has equal probability of processing a token. Now, if we assume this is the case, then this becomes the best case scenario that you can have. Now, if we multiply element by element for A and B, this is what we get: I times j for I comma j in the zip of A comma B. So we've got this, and then we take the sum of that, and then we multiply it by the number of experts that we have. So which in this case is E, which is 4. So the auxiliary loss in this case comes out to be 4. Now, if I have the opposite end of the spectrum, where it is completely getting concentrated on one single expert, right? So I've got A and I've got B completely getting concentrated on one particular expert. Oops. All right. So we've got our A and B, the same calculation goes, and then I'll get a 4. So the loss is higher for a greater concentration on one particular expert, and the loss is lower when the probabilities are diffused evenly among the different experts. So that's the whole situation with our gating function. The gating function is trying to route each token to the deputed number of experts. And then from there, once that is done, for every expert and for every slot in the top K that we have configured, we check whether the index has been selected by that expert or not, and then we process it accordingly. And we've got a placeholder here that we override with the particular activations coming from that expert. So once we have that, things look pretty simple, and you will notice that the output shapes will be coherent with the particular processing that we are doing over here. So which leaves us finally to discuss the hybrid approach, where I can take my vanilla dense FFN and then combine it in some capacity along with the mixture of experts. So we can blend the dense FFN with the MOE output, and we can parameterize with the help of the alpha hyperparameter. So the alpha hyperparameter will be a number between 0 and 1, which pays different levels of importance based on how you configure it. So as always, we've got the dimensionality of the input, the alpha. So here I'm paying equal importance by default. The multiplier will be how many more, or what multiplier of hidden neurons do I want to have against the input. The swiggloo, the experts, the top K, and the dropout, right? So we assign the alpha and we come up with the hidden number of neurons for our linear layer. And we've got our MOE over here and our dense layer over here. So in this case, I'm using a vanilla dense layer. You can go for swiggloo based implementation as well. So when we forward propagate, we run the input through our dense and through our mixture of experts, and then combine them by weighing them with the help of the alpha parameter that we've configured. So in this case, again, equal importance will be paid since our default is 0.5. So you can go for a hybrid implementation as well. So if we come back, we read very minimal, again, used very minimal necessary force to understand theory on expert routing, gating networks, and load balancing. I really wanted you to have that experience while we were running the code and looking at the output, and not get stuck in a bunch of theory. So we've also looked at how MOE layers are implemented in PyTorch. Now this, along with the part 3, which was modernizing the architecture, and part 4, which was the scaling up of training, will form the meat of what it looks like to have a production grade LLM trained. Training stability and communication, and along with combining the MOE with the dense layers for hybrid architecture. Right, so with that, I think we are done with the part 5 as well. I hope all of this is still making sense to you. We were very light in the theory, and we picked apart a very small module and study it in details. So hopefully you enjoyed this part as well. See you soon. Welcome to part 6 of the LLM from Scratch series. And in this video, we are going to focus on the second stage of the LLM training, which is the supervised fine-tuning stage. Now, all of our 5 parts have been dedicated to studying the first part, where we go through the pre-training, which is again the sizable chunk of the internet and the majority of the time and energy spent on the whole process. In supervised fine-tune, however, you will pick up a subset of very high quality data set, and then from there, you will fine-tune the model further to behave it like an assistant. Now, base models in general are just document completion agents. So if you ask a question, what it will try and do, it will try and complete the document. So it might ask a question in reply because it might think it is trying to complete a questionnaire. But what it does not know is that it needs to behave as an assistant and needs to answer the question asked. This is where the SFT stage, or the supervised fine-tuning stage, comes in, and the model starts behaving like an assistant. So without further ado, we're going to jump onto the code. Now the training and the model architectural aspects of it will be exactly the same as we have seen in the previous parts. All of them still apply. It's just that the data is going to be structured differently and propagated differently. So we'll see all of that in action. So without further ado, we'll jump onto the code. We start as always with orchestrator.py. I've got a couple of unit tests written and a train sft.py that we will use to train our model from the last checkpoint that we trained. So we're going to treat this as our base model and then further fine tune this model to come up with a new model. And then we're going to sample from it to watch the quality of the results. So I've got our train sft.py that as always starts with the arguments. So we start with the data and then we start with the checkpoint, which is going to be the checkpoint of the last trained base model, where we want to save the saved model, the supervised fine-tuned model, the number of steps, the batch size, the block size, the end layer, the end head, and end embedding should all be familiar, the learning rate CPU, and the directory of the tokenizer. So the tokenizer between these two models is going to be common. We choose the device, and here is where we load our data. So in this case, we're going to start our fine-tuning with a very tiny sample data set, and then we'll see how we can potentially scale that up to a bigger data set. So I've got load tiny HF module over here, which has a data class SFT item that contains two properties, the prompt and the response. Both of them are strings. So it goes in and tries to load this data set from the internet. So this is a standard fine-tuning set from the internet. We can have a look. So this is the data set that we are going to operate on. It is going to be a 50,000 row data set. We will not have the resources to train on each and every one of these. So we're going to take a peek at what this data looks like. In its essence, it has about 4 columns: the instruction, the input, the output, and the entire text over here concatenated. So the instruction is the actual task that you want the assistant to do. And if there are any inputs required, you provide it over here. So for example, a program to reverse a linked list with the input as list with 13579. And then the output listed as what you want the answer to be or what you want the assistant to answer with. So we're going to use all of these columns to create an instruction data set and then further fine tune our model. So with this data set, we're going to grab the instruction, input, and the output. We're going to concatenate the instruction and the input and structure it as our prompt. And the response will be the output that will be expected from the assistant. Now, if we choose not to load this data set, we are going to have our own data set. So if you have trouble connecting to the internet or this data set is not available anymore, what you can choose to do is train it on a tiny data set. We are going to do this part first anyway, because when you come up with these architectures, what you essentially want to do is try and overfit on a very tiny data set to see how it's behaving, to see how the loss is going down, and you're getting all of the expected results, and then you scale it up. So we've got the data set loaded. We're going to check some of the data out. We're going to print it. And then we're going to create a list of tuples from this. And we have this length curriculum, which will help us draw more samples from these list of tuples. So for a particular I, if I'm asking for a next item, I will stop the iteration, or I will basically grab the ith index and then return it. So this just helps us get more data to create our batch and then forward propagate and back propagate. A lot of processing is happening at this stage. So we've got the SFT collator over here, where we pass in the block size and the tokenization directory. Let's check this out. So it initiates with trying to load the BPE tokenizer. Now, if you provide a directory, it will try and load from that directory. If not, it will try to create one from scratch. And as always, it fallbacks to the byte tokenizer 256 vocabulary. I've got a property here that you can grab and check the vocab size. And then there's the encode function, which leverages our byte pair encoding tokenizer to encode text that you've sent and encode it back to a list of tokens, token IDs rather. So once you get the text, you just do self.encode and then return the IDs as a list. Now I've got the collate function where a lot is happening. So let's go through it. Now this collate function will receive a batch of data. And as we know, each row in that batch will contain a prompt and a response, where a prompt will be the concatenation of the instruction and the input. So what I'm interested in doing first is taking the entire prompt and then formatting it. Now we are going to format our data in a particular format. So here I've got the template for it. We are going to have a BOS or beginning of sequence token. And then in the next line, we're going to have instruction like so. And then we are going to add the actual instruction for that row. So this will again be the concatenation of the instruction and the input. And then it will have a response, which will be the output expected out of the large language model. And then finally, we end it with an EOS token or end of sequence token. I've got a data class here which has the instruction and the response. And for the various formatting, if I have a response associated with a particular row, then I'm going to structure it like so. So the instruction and the response are going to be plugged in from the example class over to this string template and then returned as a string that contains the instruction and the corresponding response. Now format prompt only is where you're looking to only format the prompt, which will be devoid of the response. So here, all you're looking to do is taking the incoming instruction and then structure it to be placed over here. And then the response will be blank. Now note that if you're trying to format the prompt this way, it also adds an end of sequence token, which we want to get rid of. So why do we have two such functions? Now the first function, format example, is actually the end-to-end example of the X and the Y, where I have the input instructions as well as the expected output. But when you do inference, you don't have the expected output, right? So you only have the query coming in from the user, and all you do or all you want to do is format it as per the template. And then you want to come till here and then pass it on to the large language model so that it can return the completion response. So this will basically fill up this entire section after it has been trained during inference. So we have the format prompt only. So let's come back. So what we are doing over here is grabbing the prompt and then formatting the prompt only by passing the prompt and then replacing the EOS or the end of sequence token with a blank. So typically what you would expect over here is that while you will have a row of data that has the instruction and the response, we're plucking out the prompt and only will try to structure that part. In that way, we will be able to segregate between our X and the Y. In fact, I think this will be beneficial if we run this in debug mode and watch all of the data in action. So let's actually do that. So I will have a collator coming over here, put a breakpoint, and then for orchestrator, I've got my launch.json configured. So I can simply run this. And since this runs for the tests also, I will let this pass and then we'll analyze it the moment it comes from train.py. So there's a train.py that came in. A batch of data has been collated, and then we get the first piece of text. So this batch is a list of tuples where one element, the first element of the tuple, is the instruction, and the second element is the response. So since we're using a sample data set, we will be seeing only these. So there will only be 3 data points configured over here. So the prefix text is only going to be the instruction part of it. So here we can see that, and if we really see this instruction, is that it has the beginning of sequence token, and then the instruction, and then the response blanked out. So now what the next piece does is it formats the entire example, which has the X and the Y, which is the instruction and the output. So we're going to grab our text and watch it in our text data set. So this contains the response, the expected response, as well as the end of sequence token. So we have the prefix text and the full text. Now we're going to encode the entire text. So we can watch these IDs unpack over here. Now these are going to be the prompt IDs of this entire text. So our beginning of sequence token has an ID of 0, and our end of sequence token has an ID of 1. And we can check this out by grabbing the vocabulary that we have chosen to use on our part 4. So if you see ID 0, a beginning of sequence and a special token is true, and with the ID 1, I have an end of sequence token. So we get the prompt IDs over here as well. So these will be the IDs for the various prompts, or this particular prompt rather. So while this is for the entire response, this is only for the instruction without the response and the end of sequence token. So you see, you have the response over here and the end of sequence token, which is missing over here. All right. So from there we step over. Now I've got the length of my prompts, which in this case is 24. So I have 24 elements over here. I'm going to take a copy of the X and the Y. Now what I'm interested in doing is I wish to configure Y from this so that it first of all gets rid of the entire prompt. So I'm going to get all of these elements which are part of the original user input and then replace them with -100. Now the -100 is the ignore index in PyTorch, and what it will do is that once you pass a -100 as the index, PyTorch will actually ignore this particular positions while calculating the loss. So what you want to calculate your loss on is the completion tokens that the model output, not it trying to complete the user input, which is already available at my disposal. So I'm going to grab all of these input tokens and replace them with -100. So this is going to be a for loop, and then the Y is actually going to be a shifted form of the X. So if you have the entire text as your X, you want your Y to be shifted like so, right? So for every input token X, you want the corresponding next token to be Y. So what we are doing here is right shifting all of our tokens, and then finally we'll be left with the last token, which we again need to ignore because it will not be part of the response. So we are right shifting over here, and then we are masking or ignoring all of the prompt tokens over here. So once I do that, my X is going to be the entire input plus the output, and my Y is just going to be the outputs only. In that way, I will be able to calculate the loss for these two particular tokens in this example, and then I will be able to back propagate from there. So we can run it till here. And then what you see is that the Y now has been converted, and it only has tokens turned on in these areas where I'm expecting. So for the token 203, I will be expecting a response of 22. For the token 22, I'll be expecting the response of 1, which is the end of sequence token, and then this gets ignored, and so does everything before that, which is going to be our actual prompt. So this is going to be our Y, and X is going to be the entire input plus the output. And in this way, when we correlate this X with this Y, we will only compute the loss in these positions so that we can judge our model based on the completion tokens only. So that's the way we're going to structure it. And then finally, for this batch, we have the X and the Y coming in. So I'm going to disable this breakpoint right now, and I'm going to try and run till this line, and then we can continue. So our collate function run, and what it has, will take a final peek into this. So this contains the entire batch of data. Now, what I've also done here is this is going to be all of the input along with the EOS sequence. Now, since I've got a block size of 256, in order to maintain consistency across batches, because different prompts will be of different lengths, I need a padding token. And I've chosen 2 as the padding token. If we go back again and visualize our vocabulary, you will be able to see that I have a special padding token configured over here whose ID is 2. So you can take a look, and this is exactly what it will behave like. All right, so this is where I'm saying pad all of the tokens till the block size to 2, and then for the rest, for the Y, it will be -100, the ignored index for PyTorch. So here we've got the XB, a batch of input and output padded, and then we've also got YB, which is going to be a batch of all of the indexes. So for the first example that we saw, only these 2 tokens will be turned on. For the second example, we have these, and for the third example, we have these, right? So everything else will be ignored. So we're intentionally doing it with a very tiny data set so that we can really visualize what is going on. So we transfer it to the device, forward propagate our pre-configured model that we have imported from part 3, and we haven't attached all of the bells and whistles. So this will have KV cache, but for example, we haven't configured sliding window attention and attention sync in this particular instance. So we go through the logits and the loss. We're going to step backward, and this is where you can also come in and say you want to have a mixed precision training. You also want to enable gradient accumulation so that we can go for a better batch size. Again, I have tried to avoid all of the clutter so that we can hyper focus on the data structure for the SFT piece. So we're going to step over here, and for every 20 steps, we are going to log the loss. So once we do that, we're going to hit tosh.save, and then we should be good. So this should ensure our training completes, and we will have the supervised fine-tuned model at our disposal. So with that, let us actually proceed towards a full-blown training rather than running it in debug mode. So we're going to stop it. We've pulled up our terminal, and then we're going to train on a sample data set. So it goes through the tests where I've written tests for formatting and the masking happening. So I faced a lot of bugs while configuring the test masking part, because you had to right shift the Y, and then from there you also had to make sure the right tokens were padded. So first things first, we print a sample of our data, and then we're going to load our trained tokenizer from here. We're going to load our last checkpoint of the base model from here. We fine-tune it through a bunch of steps. We save it. Again, since this is only 3 examples, it is going to overfit. And then from the Python sample sft.py, we are going to sample the data. So I'm asking what are the 3 primary colors, and the response comes as red. And then various questions that have already yielded the correct answers, even a coding question. Now we'll check these out in detail. So let's proceed and see what the sample SFT does. So now that you have the trained model, it's essential for us to understand that you also need to sample, or you also need to run inference on it. And there's a lot of data processing involved to make sure that it is in the right structure so that the assistant can respond in a certain format. So here we will pass the checkpoint of our trained or fine-tuned SFT model. We're going to take the prompt from the user. The block size and layer and head embeddings are all part of loading the model checkpoint. How many tokens that we're looking for, and notice that you'll notice we've also implemented early stopping. So if while generating tokens, the model encounters an end of sequence token, we're going to stop there. We're not going to generate more tokens from there. This is because our data has been configured to stop at EOS. So if the EOS goes as input to the model, it might output junk from there. Things might not make sense. And of course, I'll also have to provide my tokenizer over here. So I'm loading my checkpoint. I'm running my SFT collator, or initializing my SFT collator. GPT modern is the exact same thing as we've done in part 3. And we're loading the state dictionary, putting it on eval mode. And then the prompt that I get from the user will go as an argument to format prompt only. And if you look at format prompt only, it provides you with this format. It will give you everything till here, but it won't give you the response, since that's what we're interested in generating. But then it will also provide this as the end of sequence string is a part of this template. So what we need to do over here is remove it so that the model can go on to completing documents. And then if it generates an EOS token, we're going to stop. So we're going to take the prompt text and encode it, and we get back a list of IDs. We're going to convert that to a torch tensor, and then we're using the generate function over here with all of the input index, the max new tokens that are configured, the temperature, and the top K. We've seen this all before, so we probably do not need to double click on this. Now the model will spit out an output, which we will convert to as a list. And then if it is coming from our tokenizer, we will decode it, and then we will print the generated text. So it's pretty simple, all of the things that it is trying to do. So if I run it again, and since we've already trained our tokenizer, we don't need to wait for it. So our sample sft.py grabs the checkpoint from the last trained model with the block size, end layer, end head, and embedding that are familiar. Now I wanted to add a quick note on the context window, and this I'm sort of injecting after I'd recorded the original video because I'd forgotten to mention it. So you will notice that during the SFT phase, you can actually have a different block size or a context window compared to the base model. This is because the matrix, the way they are configured, it works out. So the same model with the same weights can be trained in 2 separate stages with 2 different context windows. What does this do? First of all, it's a nice feature to have. Second,
with the base model with a lot of data and throwing a lot of compute, you might want to train it with a lower context window. But during the SFT stage, when you're only going to be working with a subset of the training data, not in the scale of millions, but in the scale of thousands, you might want to increase your context window at that point. So this is where a base model trained on 8K context can become a 64K context model during the SFT phase. This helps us seamlessly expand on the context window without compromising a lot on the cost and compute. And then for the prompt, we're sending what are the 3 primary colors, and notice that this is also part of our data set. And we're only using a sample data set. So first prime number, what are the primary colors, device name, which points to direction. So we've got our data set over here, and we've got some questions configured over here. Some of them are from in sample, some of them out of sample. And you can see that since this is only trained on 2 or 3 data points, from in sample data, it answers correctly. But when things go out of sample, it still tends to fall back on any particular token, right? It does not answer questions correctly. So I was asked to reverse engineer the factorial code, and that's all it gave, right? So we're going to scale it up and see if it changes or not. But before doing that, I really also wanted to zoom in on the sample SFT and how this works. So we're not training anymore. We're just interested in understanding how the sample SFT works. So I'll put in a breakpoint over here, and then we'll try and debug it so that we can visualize it together. So we tried to run the sample SFT directly, which won't work. We'll have to start from the orchestrator. Then after running the tests, we are in sample sft.py. So we're going to step over. This is going to be the checkpoint, and where I've got the model loaded from the previous run. I'm going to grab all of the configuration. So the vocab size, block size, layer embeddings, etc. All of the rope and swig and all of the stuff. This is going to be our collator, and this is going to be our model. We're going to load the state dictionary of the model. So basically the weights, I'm going to put it in eval mode, and then prompt text will be the arguments.prompt, but formatted. So if you look at it, the prompt is the raw question that was asked. What are the 3 primary colors? Here, once I step over, the prompt text becomes the instruction fine-tuned version. So it has the beginning of sequence token, the instruction, and the response with a placeholder for the LLM to complete it. So we're going to encode all of those IDs, convert that to a tensor, and then let's actually step inside model.generate. So we're going to step into this and see what happens. So we are inside the generate function where we got a model. We got the input tensor, we got the max new tokens that we want to sample, the temperature, the top K, the top P, the EOS ID. So this is something that we are seeing over and above what we have seen in part 3 already, because we're interested in early stopping. Then we are not using sliding window and attention sync. So from there, we do our imports, put the model in eval mode. The prompt is going to be the IDX. So this is going to be the sequence of token IDs that we have as our input. Our KV cache is going to be initialized for the 2 layers that we have as none. And this is going to be the first generation. So this condition will get invoked, not this one, because we haven't produced any token yet. So we're going to step over. The ID condition pretty much contains all of the input IDs against this prompt. So this is going to be the beginning of sequence token. This is going to be new line, and then 3 hashes follow like so, and then it goes on like this till the last new line, which is over here, right? So the starting position for this will be 0, and then finally we forward propagate with no KV cache, since this is the first invocation. So we get our logits. Now, since I get logits for each and every prompt and its corresponding prediction, I'm only interested in the last completion token. So I grab the last one, step over it. I'm going to do my top K, top P filtering. So we will be able to see the difference on how the top K stabs everything to 0. So let us grab our next logits and try to visualize it here. It's a tensor full of logits for, should be of length 8000 because that's our vocab size. And then from there, after the filtering, the next set of logits, now pretty much everything becomes infinity. There'll only be 3 tokens which are turned on. So in order to really confirm this, so I've got the next logits over here, but if I filter it out by next logits that are greater than float of minus infinity, then I will be able to get 3 such logits, right? So our temperature is not configured to 0, it's 0.2. So there will be a sample drawn from one of these 3 tokens as per their probability distribution. So this is where we compute the probabilities. So if we step over and look at it from our debug console, it will also be a bunch of zeros, but then if we filter out, there will be 3 probabilities where one particular token has an abnormally large propensity, and then there are 2 very tiny such probabilities. So from there, I actually grab my next ID based on the sampling technique, and the next ID is going to be 744. And then if we go look at our vocabulary for 744, so the question asked was, what are the primary colors? And it seems to be that it has correctly predicted red. So from there, we check whether it's an EOS token or not. So the next ID is not going to be the EOS ID in this case because 744 not equals 1. So it does not enter the break and it continues to generate. Now this time, however, we are going to have KV cache at our disposal. We can again confirm this by checking out the KVs. A KVs is a list of 2 KV cache elements, one for each layer, and each KV cache data class actually contains 2 tensors, one for the K and one for the V. So from there, we step over. Our starting position is this time going to be 31 because we had 30 tokens in the input and we've generated another token, another completion token, which makes it 31. So our model is going to start generating from the 32nd token onwards. The KV cache is filled up, and this time we are only going to send the last token as the input. The rest of it will come from KV cache. So we go from there, the next set of logit probabilities, and then the top K filtering, the probabilities. And then again, if we look at our probabilities now, this will be concentrated on one token, again having a lot of propensity to appear. So our next ID now becomes the tensor 1, which is the EOS token. So this time we will break out of our loop and it actually enters break because it has hit the EOS sequence. And then from there, it will return the entire sequence and we are back to sample sft.py. And then from there, it takes the output, decodes it, and then prints the generated text onto the console. So we can let the program run from here, disable the breakpoint. And if we come back to our terminal, we will notice that all of our output has appeared. So that's the part where we have completed one tiny sample training. Now what we're interested in doing is actually scaling this up slightly. Now, for all intents and purposes, you can actually do a full-blown instruction fine-tuned dataset, but we still don't have the resources on our laptops to train an entire SFT model. So what we're going to do is give you a flavor of the scaled up version. So we've got the alpaca dataset for the IFT or instruction fine-tune, or the SFT, supervised fine-tune dataset. We are going to actually load that by setting sample dataset equals false. And then we're going to load 24 data points from it. And then we are going to sample 3 questions this time, again, that was part of this dataset. So while our toy dataset answers the question, what does DNA stand for, with either compass or red or stuff that it has seen in its training data before, this time the training data will be aligned to the Hugging Face dataset, and it should give us the right answers from here. Now for that, obviously we need to train our model because the data has changed. So we'll put it back on training. We'll clear the console and then rerun the entire thing. It runs the tests, starts running the train. It has printed a batch of data. So it has a bunch of questions and answers configured. And then from there, it starts optimizing. Now we started off with a high loss, but we can see that the loss is healthily decreasing. And then from there, once we sample, so what are the primary colors? This time it says the 3 primary colors are red, blue, and yellow. What does DNA stand for? DNA stands for deoxyribonucleic acid. And then even if you ask it to write a program, it will actually do so as part of your response. Right? So as per the instruction fine-tuned dataset that you have configured, we are able to see that the model has started responding. Now, not anytime soon will this particular model become intelligent. We've only got 2 layers of transformer blocks at the end of the day, but hopefully you get the flavor of what a production grade SFT looks like. Now, in the real world, you would probably take a base model that someone else has trained, and you might want to go for a LoRa fine-tuning, or you might even want to take the instruction fine-tuned version of a model from the internet and go for a LoRa fine-tuning. There are just too many good resources on the internet that already covers LoRa fine-tuning. So we've decided to skip this as part of this particular series. And after all, this is called LLMs from scratch. So we want to check out each and every element and module that happens from scratch and not build on top of anything as much as possible, right? So with that, we come towards the end of this part. So in our supervised fine-tuned model, we covered the instruction dataset formatting, the causal LM loss with masked labels, the -100 ones, the curriculum learning that structures it into tuples for instruction data, and of course, evaluation with the sample SFT. I hope you had a lot of fun learning this. Thanks a lot. Welcome to part 7 of the LLM from Scratch series. And in this video, we're going to explore the 3rd phase of our LLM training, which is the reward modeling part. Now, the idea over here is once you've pre-trained your model and then supervised fine-tune your model to behave like an assistant, what you want is the model to be free of biases, and you want to align the model to your preferred responses. So for this, it's a 2-part process. First things, you need a reward model that will output a scalar that will depict a reward for a particular instruction prompt and a response pair. So if there's a question that was asked and there are 2 answers, one has a higher reward than the other, then that reward is more preferred than the previous one. So the core idea is that typically you will have an instruction based on which you might have response 1 and response 2. Now, based on this, you might want to prefer this one over this one because this might be more neutral in tone, or you're trying to calibrate your model to a certain persona, whatever your human preferences. So as per your human preferences, you have an instruction prompt and you have multiple responses against that instruction prompt. And what you're trying to do is choose one over the other. Now, this is a stage where you will typically have data sets that are a little north of the instruction fine-tuning set, a little bigger than that. And here is the stage where you'll spend a lot of effort, maybe hiring contractors and experts and even having advanced degrees in their fields so that they can label the data properly. Now, what it serves as an outcome is that you will have a model that takes in an instruction prompt and a response and outputs a scalar depicting the score for that particular pair. So for implementation, what we are going to do is that we are going to go to the route of the encoder only transformer. So while you can totally use your LLM, so let's say there's your existing LLM with the decoder only architecture stacked up, what you can do is after the layers are done, maybe snip it over here and then add a classification head or a linear head that only outputs a scalar. Now this is possible. What we are going to do in this video, however, just to give you a diverse flavor, we are going to take this part of the transformer and then implement it. So this part is the encoder part. Now what this enables us to do is that the difference between the encoder and the decoder mainly is the masking part. So the decoder cannot have access to the future tokens, right? So, but the encoder can. So when you're looking at an instruction prompt and a response, you want to have access to the entire thing, even if you're sitting at token 1 or token 2, you can have look ahead. So that's why we will prefer implementing the encoder only architecture. And then from there, once the encoders are stacked up, we will look at mean pooling. And then finally, a linear head, which will give us the scalar scores, and then we'll back propagate. Couple of things we'll learn along the way. So we'll learn Bradley-Terry loss, and we'll also look at margin ranking loss. We will use Bradley-Terry loss in this, but we will also look at we've also implemented margin ranking loss in this. So just to summarize, this is what we are trying to achieve. So a prompt goes in, it goes through the token embedding and the positional embedding. We are going to keep the implementation of the encoder only reward model to the vanilla transformer architecture. And then from there, I'm going to attach a linear head that simply gives a score. So this is going to be our preference score. And then we'll calculate the loss as per Bradley-Terry or margin ranking and then back propagate. That's going to be our core architecture. So we'll jump on to the implementation now. So we have our tests as usual, and then train rm.py, where we are going to train our reward model for 300 steps, batch size of 8, context length of 256, 2 layers, 2 heads, and embeddings, Bradley-Terry loss, and we're going to reuse the tokenizer. So you see all of the hyperparameters that we're using are highly aligned with the previous ones that we have seen before. Usually this might not be the case. So if you're trying to implement an encoder only reward model, you would have a much more shorter or much more truncated version of the original LLM, orders of magnitude lesser, because the task at hand is to preference score, which literally gives out a scalar, and you don't have to go through the nuances of perplexity and outputting one token at a time. Right. So the best way I have seen as per the last part is to run it in debug mode directly. So we're going to put a breakpoint here and then propagate through it ourselves. So we have our orchestrator running, and then this is running for the tests. So we'll just skip it and wait till we reach our train rm.py. So we've reached our device over here, and then from there we forward propagate. Now in this load preferences, the style of collating the data is going to be very similar to the previous part. So we'll just step into it and look at it. So we've got a split. This can either be train or test. And then this time we are trying to load Anthropic's RLHF dataset. Let's take a look at it. So here's Anthropic's RLHF dataset. There are two splits, train and test. And for each one, there are only two columns, chosen and rejected. So if I were to look at one of these, there's an entire context, the instruction and the prompt, and even in some cases, the history of the conversation. And then all you have to do is rate one over the other. So this is the chosen one. This is the rejected one. And this is as per the alignment or the preferences that you're looking for in order to build your own large language model. So some might like a more fun persona. Some might want a more neutral persona. Some might want to avoid political biases and so on. It's really based on human preferences. So from there, we get the chosen and the rejected columns, and then we append it to our preference example. So if we just run through this, we've loaded our data, and then we're sampling our data. So the chosen one is this, and the rejected one is this. So some of the cuss words won't be appropriate to show you over here. And we keep on appending the items, and this we're going to continue doing for, I think, hundreds of rows. And if not, we've always got a fallback, and I would prefer you use this one first and overfit and make sure that everything runs till the time you scale it up to the entire data set. So we've loaded our preferences. Now we skip through it fairly quickly because we have seen this implementation before. So we organize this into triples, where the prompt will always be blank because we've chosen a data set where there is no instruction prompt and then the task and then the response, right? So all of the instruction prompt and even the conversation history has all been concatenated into one. And that's why the prompt is going to be blank. I've intentionally kept a placeholder because if you have a data set that has a separate column called prompt, you can kind of use this as a scaffolding framework. So we get to the pair collator now. Now this is just the declaration part. So we'll take a peek at it. And this will be very similar to the collator that we have seen in the previous part before. So we have the block size, loading of the tokenizer, and that's all the elements we need. We have the vocab size property. The encode will just be a wrapper around the encode function of our tokenizer. And then in the collate function, for every prompt chosen and rejected in our batch, so we are unpacking this particular tuple from the batch. We are formatting our example as per the prompt chosen and the prompt rejected. So if I were to look at the format example, you will see that it is the exact example from the previous part. So here I've got the formatters.py, and this will format example as per the template that you sent. So as long as the example getting sent has an instruction and a response strip, we should be fine. So we format our example like so. So there's the positive text and the negative text, and we format it as per our SFT template. And then we encode, and then we take everything till the context window. So if the text spills over the context window, we'll just clip it there. And if it doesn't, we are going to pad it with our padding token, which we already know is 2. So if we again go back to our tokenizer quickly, you will see that the padding token has an ID of 2. So we try to pad till the block size. Again, if it is less than the block size, it will pad with 2s till our block size. So we have the positive and the negative here converted to a tensor, and then we return them. So I'm going to skip over this because this is just a declaration, and this is our reward model. So it has certain elements and they are very simple to understand. So we have the vocab size and the block size, the token embedding, the position embedding. Again, think vanilla transformer. And then there's a transformer encoder layer. Now, literally the difference between this and what we've implemented in part 2, part 3 for understanding vanilla transformer is that the masked layer is missing. So this gets access to the entire attention block, including the future tokens. And if you see, some of the hyperparameters are also very similar to what we have seen in the past. So even if I were to open the package up, it literally says implements the original architecture described in attention is all you need. So we're going to reuse PyTorch's transformer encoder layer, and then we are going to stack up one such layer over n number of layers as per however many layers I pass. So this we will pass as 2 in our case. So what this does is transformer encoder is a stack of n encoder layers. So I will have to pass the architecture of my single encoder layer and then specify how many such layers I'm looking for. There's a layer norm and then there's a linear head. Now we'll check this out during the forward propagation. So let's come back. So that's a model declaration. It's a pretty simple one, encoder only transformer with eventually a scalar head for measuring our preferences. So we enter into the training loop and then we grab a batch. Now, if we were to look at a batch, this is what our batch looks like. So it's again a list of tuples. We have seen this kind of format before. So from there, we get to the collate function. Now let's actually dig down deep to see how the collation happens. So we've hit the collate function in our pair collator, and for every triplet we go in, our prompt will always be blank because that's our data set. So we've got the positive text and the negative text. So here is where we have the positive text, and then here is where we have the negative text. Now notice that these are aligned with the SFT format, where I have an EOS BOS token, and then from there I have the instruction as well as the response. Right? So from there, I'm going to tokenize my positive and the negative IDs. We continue doing this for all the examples in our batch. And then we entirely encode the positive and the negative. So if I were to see this, the positive shape, so these will be, each will be a sequence of tokens. So there will be 256 tokens as per our batch size. And then the batch size itself is 8. So our position or positive shape should be 8 by 256. And the same obviously goes for the negative one as well. So this is returned. And then we transfer it to our device if you're using a GPU, and then we forward propagate. So let's actually check out what happens inside. So we get an 8 by 256 sequence. So our batch size is 8 and our token sequence is 256. For calculating the position embeddings, I'm going to do an A-range over 0 to t. So this will literally be a vector that has 256 elements starting from 0 to 255. And then from there, we're going to unsqueeze it. That means adding one more dimension. So you see, this becomes the POS array becomes a 2D array because I've added the unsqueeze, and it's literally 0 to 255. So let's proceed. Now with that, I'm going to take the inputs, calculate the token embedding, take the A range, calculate the position embedding, and then add them together. This is also something that you've seen in a vanilla transformer. Now, there's an important part here. Although we do have access to future tokens, since we are going to pad each and every sequence with the pad token, with the special pad token, we don't want the model to look at a pad token and make decisions. We want the model to ignore it. We are only adding the padding because we want to adjust all of our dimensionalities to represent, so that everything represents the context window, and then the matrix math can happen. But we don't want the model to concentrate on the padded tokens. So that's why we make a mask, and we are aware that as per our tokenizer, the padded token has an ID of 2. So we create a mask, and this will produce a Boolean where it will say that if we see a padded ID, then we turn it on, we say it's true, otherwise it will be false. So if you'll see this tensor, elements towards the ends are all true. So from here, we forward propagate through the encoder, and then we ask it explicitly that source key padding will be this. So it's aware that what the padded tokens are, and it learns to ignore it while connecting or while calculating the attention scores. So we forward propagate it through that, which is again our encoder layer here, which is a stack of transformer encoder layer, a vanilla implementation of the encoder layer from Attention Is All You Need paper. So we've done already all of this already before. So we're going to proceed. Then a layer normalization. So if I were to now look at H and what it is. So there are 8 data points coming in. Each of them has a sequence of 256. Now each token itself will have an embeddings that are 128 vectors, right? So at this stage, the H should have a shape of 8 by 256 by 128. So as expected, we are seeing that 8, 256, 128. And then if we forward propagate it through our encoder, the shape should not change. So that's good. If we layer normalize, the shape will not change. Now from here, I'm creating a mask so that I can do what is called a masked mean pool over tokens. Now, if you've seen a use case in RAG before, then this might be familiar. Let me try and explain. So we've got a batch of 8 coming in. So each of this can be thought of as a sequence of 256 tokens. Now each token in turn has an embedding length of 128 each. So there are 128 elements here. Now what I'm interested in doing is that I'm coming up with a pooling layer. And this is again very popular for if you want to have multiple chunks in your retrieval augmented generation architecture, and you want to go through masked mean pooling to represent them as a single embedding, or in this case, reward modeling, where the entire 256 sequence can be represented by a single embedding so that we can forward propagate more efficiently. So we have 256 such propagations. Each of them is a vector of 128. Now what I'm interested in doing is that I'm going to take away all of my masked tokens. So let's say a few tokens here, and after that, these are all masked. So I'm not interested in looking at them. So for the non-masked tokens, I want to calculate the mean or the average. Now, once I do that, what I will have along this dimension, I will have a single 128 embedding vector that represents this sequence. So although it was supposed to have 256 tokens, I've condensed all of that by averaging all of the embeddings out to represent them by a single embedding, which has the dimensions of 128. And then from there, we are going to attach a linear head to these 128 vector embeddings, which will eventually output a scalar, which is my preference score. So let's check that out. So I'm creating a mask where I'm flipping the bits for the padded mask. So in this case, if a token was padded, then it was true. And in this case, if a token is padded, it will actually be turned off or it will become false, which when represented in float actually means 0. So that when I apply my mask to my age, the tokens that are padded, they automatically turn off. All right. So if I apply the mask now, so for every token, you will have a Boolean which says true or false. So if I look at a mask shape, I'm looking at 8 by 256 by 1, where it represents each token, whether it is padded or not padded. And then when I multiply this matrix with our H, 8 by 256 by 128, I'm going to get, or what is going to happen is I'll still get a 8 by 256 by 128, but wherever I see a mask token, the 128 embeddings will all be turned off and converted to 0. So if I were to look at H times mask, then you will see that whatever tokens are not the pad tokens are still visible, but then whatever tokens are pad tokens are all converted to 0. So that when I now take the pooling, it doesn't matter that like these won't have any say in the calculation of the mean, right? So now I'm going to take the sum along dimension 1 because again, if I look at the H shape, this is the dimension 1, the 256. And what will happen is you will have a representation for a single sequence. So you will have 8 representations of 128 vector embeddings each. So each sequence of 256 tokens gets compressed to one single 128 vector representation. So I'm going to go through this 8 sum. And now if I look at 8 sum, it should be 8 by 1 by, my apologies. So if I look at the dimensionality of 8 sum, it should be 8 by 128. So it will have 128 vector representation for each sequence in my data point. So from there, I'm actually calculating the average. So I'm taking the length, and for taking the length, I'm going to sum up my mask. So what this does is that whatever is false gets counted as 0, but whatever is true gets counted as 1. So I sum it up. I will get the count of all of the non-padded tokens. So mask.sum will give me all of the count of the non-padded tokens. And if there are no non-padded tokens, I'm just taking a minimal of 1 to avoid zero division error. So the length in this case, if we look at it, will be 256. So the first sequence does not have any padded tokens. That's what it means. So if I were to look at the len, then for each of these 8 sequences, then you will see the number of non-padded tokens that are there. So here we go. So the pooled will be the 8 sum divided by the length. So we're normalizing, taking the actual mean. So the pooled now will be 8 by 128, but this time normalized by the length of the non-padded tokens. So from there, I've got a head, which is nothing but a linear head that takes in an n embedding, which are in our case is 128, and then gives out one single scalar, which represents the preference score. So we've got R over here. So you see, R will be 8 scalars representing the preference scores for each of the sequences in my batch. So I return from there. So we do this for R positive. The same goes for R negative. And then we do another forward prop for the rest of them. So we might want to come back and take stock of where we are. So we want to come back to our training loop. And now we'll see that the R positive and the R negative for a batch has been set. Now, in an ideal world, what you want to do with these preference score is basically compare them. And you want your positive example to have a higher preference score than your negative example. So this is higher than this, so we're good. This is also higher than this, so we're also good here. And you see, whenever we won't have this particular situation where the RPOS is greater than the RNeg, then we should impose a high loss. So for understanding that, let's go through the Bradley-Terry loss. Now here, what I'm interested in doing is I'm taking the difference of R positive and R negative. Now, if it is the case that RPOS is greater than RNeg, then this diff will be positive, and then I'm negating a positive. That means this will be negative, and soft plus applies this particular function, which has this curve, and you can see that for a negative number, the output tends towards 0. So it's a smoother function compared to your ReLU. And you can see that if the positive is greater than my negative, so let's come back and study this carefully. If the positive is greater than my negative, it makes the difference a positive number, and I'm passing minus diff, so I'm passing a negative number, and negative number means the loss will be 0. And if the margin between the positive and negative is further above -2, then it will be a hard 0. Otherwise, it will have some loadings over here. So I'm trying to incentivize my model to have a large margin classifier and have a lot of score difference between the positive and negative. So that's Bradley-Terry loss. Now, there's another loss called margin ranking loss, where we have, so we are passing it over here, the R positive and the R negative. We know for a fact that we are passing the R positive first. So we set the Y equals 1. So whenever the first score has to be greater than the second score, the Y has to be 1, or it will be flipped if the opposite is the case. Now the margin ranking loss is governed by a simple equation. So we take the max of 0 and minus Y times x1 minus x2 plus a margin. Now the margin is optional. It can have a value of 0. In fact, the default is 0. Now, let's look at what happens here. So since we are expecting that x1 should be greater than x2, so our RPOS should be greater than our RNeg, we can assume that Y is a 1. So if Y is 1 and this yields a positive number, then this becomes negative, and the maximum of 0 and a negative number is actually 0. So our loss is 0. Now, if it were flipped, if x1 has a lesser score than x2, this will be a negative number, and the negative will cancel out with this negative. So this whole expression will become positive, and then that will be the output of the loss, resulting in a higher loss. So that's the way it's structured. So whichever loss you want to look at, you want to take the positive loss and positive reward score and make sure it is greater than the negative score. And you want to have a loss function designed to incentivize that behavior. So in this case, we're going to, let's really go into it and check it out. So we've got our RPOS tensors for the batch of 8 and the RNeg tensors for the batch of 8. And then from there, we step in, we've got our diff. So in this case, whenever it's negative, when the diff is negative, we will have a loss calculated. So soft plus mean, we are actually taking all of the calculations of the losses. So we should probably hand calculate it on our own to check out what is going on. And you can see that whenever the difference is large, we actually incur quite a loss. So for example, minus 0.1101, yields a loss of 0.74. But then smaller differences also incur some loss because of the soft plus. So if the difference had been large enough, then we would have incurred zero loss. This is why we're using soft plus, so that we can use a large margin classifier. So from there, backward and then back propagate, and then we print out everything. And this should take care of our entire training loop. So once we have our training done, let's actually evaluate what happens in the eval. And it's pretty simple. So we'll let our training continue. So the training has started for us. So every 25 steps, I'm logging the loss. And you will see that it is jittery, but overall it has a trend of learning. So we've gone through our training loop, and now we are in the evaluation loop. And we're going through our device. The load preferences this time will be dictated by the split that we got, which in our case, we've got two evaluations. So one for train, one for test. So this is going to be our train eval. Loads all of my examples. So we've got the triples over here. The collator, this time I'm loading the checkpoint. And then loading the state dictionary, putting it in eval mode, doing it for batch of 16. So I'm collating my positive and negative, and then from there forward propagating. And then whenever the rpos is greater than rneg, I'm assuming it's a correct example. So I'm counting my totals and then doing it for however many batches I have. In this case, I only had one batch because the batch size is 16 and I only have 8 examples. And the accuracy is that we are correct 6 times out of 8, which is nice. So we print it. Then we look at our terminal. Then we'll see that, okay, this is, I think, the second eval. So we'll just let this continue. And all of our checks are complete. So for the unknown pairs, we are at an accuracy of 50%. For the known pairs, we are in an accuracy of 75%. Now, if I were to show you this as one full flow, then things would start making sense. So we've got the test for the BT loss and the reward forward. I'm training. So here it will go through the different steps. We are only training on 16 data points, I think. So we can't expect much and the loss will be jittery. But in general, the reward model piece is, again, anything to do with the RLHF, the reward model, or the PPO part is going to be sort of very tricky to converge. But we can't judge the numbers based on this because, again, only 16 examples, 2-layer neural network. But again, if you take this and apply it on a larger data set, things would start making sense. So you see that while our training accuracy is 75%, this is even worse than a coin toss. So didn't really learn anything, but hopefully with scaling up the number of layers and the number of examples, a lot of things will happen. So this brings us to the end of part 7, where we went through preference datasets, the reward model architecture, the loss function, and we really went into the debug mode for all of the for analyzing all of the shapes. Hopefully you had fun learning this one. Thanks a lot. Hello and welcome to the last part of LLM from scratch. And in this part, we're going to cover reinforcement learning, specifically the proximal policy optimization technique. If you've made it this far, congratulations. There's just one more part to go. and then you'll be completely familiar with all the phases of a production grade LLM and how they are trained in the real world. Now, before we start, there are some terms we need to get out of the way. And in no means is this going to be an exhaustive lesson on reinforcement learning and its corresponding theories, but we'll have to know enough about these terms in order to go implement our PPO. The whole subject of reinforcement learning is pretty vast in theory, so we will barely be able to scratch the surface. But of course, as and when these terms spin off, I'm sure there'll be further reading to do in this area that is left as an exercise. Won't be covered as part of this video scope. So the first things first, I want you to be fluent with some terms we use throughout the video. So the state. Now, in the context of LLMs, the state is the current state that you're in, the current text context. So let's say you come in with a prompt and then you start the LLM inference or the generation. The prompt itself becomes the state. So if you have 30 tokens coming in as the prompt, those 30 tokens become the state. And then when you generate another token, that new token gets added to the existing 30 tokens. And now the 31 tokens go as input to the next step. So the second state of the LLM becomes those 31 tokens. So the state will change over time. Now the action is the actual action of the model predicting the next token. So this will be at the 30th step once the prompt comes in. When I predict the next token, it's called the action. Now at any given stage, I will have, as per our vocab size, 8,000 options to select a particular token. So every action associated with the state will be considered when we are trying to do proximal policy optimization. So it's a specific context and the specific next token chosen in it. Now the policy is literally the LLM that we will build and update to align it to human preferences. So this is going to be the actual decoder only LLM that we have built so far. Now the value is the predicted total future rewards that I will get given a particular state. Reward is a scalar score from literally coming from the reward model. So this will be a proxy to the human preference or the human score that we'll get given a prompt and a response pair. So now let's say there are a few tokens going in as input, and then I predict the next token and the next, and this constitutes my prompt and response. Now we will receive a reward here at the end of the generation by the reward model. But at this stage, the value of this particular state and action or this particular state will be the estimated future rewards that I'm going to get. So at this stage, we will try and estimate what reward we might receive if we continue this generation using this policy. So it's going to be a future prediction or an estimation of my cumulative rewards. Now, we know for a fact that we only get a reward at the end of the answer or at the end of the generation. So we'll try and estimate that through the value. Now this, in our implementation, will literally be one more node to our LLM. So our policy will now have two components: the LLM that does the actual generation plus a value head that is a scalar that literally predicts value. Now the returns is the discounted sum of future rewards for the rest of the generation. So simply put, if I complete a particular generation, the rewards that I get at the end of it or at the end of a batch can be summed up and can be considered as the total returns. So our value or the estimated prediction of the total rewards will have to be as close to the returns as possible. So this is where we'll use the value and the returns to calculate the value loss. So we'll watch all of this in action. The Q value is the expected return if we emit a token at that point. So again, given any point, I will have 8,000 options, and I can I can consider the fact that given these 30 tokens, what if I generate token 1? What is the Q value there? What if I generate token 2? What is the Q value there? And so on. We'll obviously not be doing all of these calculations, and it will all be an estimation that we'll see in a minute. Now, there's a new term, advantage, that is simply going to be the Q value minus the estimated total value at that state. Now, the KL divergence is a general term. If you're familiar with stable diffusion or variable autoencoder, you might have seen this. But in general, if there are two probability distributions, then it measures how divergent these two distributions are. Then finally, we have the policy and the reference. Now, these will be literally two LLMs. So the policy LLM and the reference LLM will start at the same point, which is the frozen SFT weights that we will import from part 6. And then from there, it will go through a reinforcement learning iteration, and the policy will keep getting updated and the reference will be frozen in time. So what will happen is, after every update step, I will actually measure the KL divergence between my policy and my reference model. And I might actually even take some actions based on how far apart these two probability distributions are. What reinforcement learning does to the LLM is that it aligns it to the human preference, and in pursuit of doing that, it may diverge far away from the SFT fine-tuned stage. So KL divergence is a measure to, number one, track it, and then number two, using that, we may clip our gradients, we may clip our updates to reflect stability and to achieve better convergence, to not deviate a lot from the SFT, to not have what is called catastrophic forgetting. So with that quick set of definitions, we'll jump onto the code. We'll keep revisiting these definitions as and when required, so that you can keep remembering, and all of these terms have a high recall in your head. So we have a train and an evaluator. We'll start with the train. So as always, we'll start with the debug mode so that we can actually visualize our inputs going through the various pieces of code. So here we have our different arguments, very generic, the top ones especially. So the policy checkpoint will be our SFT frozen weights. The reward checkpoint will be our reward model that we trained on the last part, the number of steps, the batch size, block size, and a couple of other new ones that we'll explore in a minute. So we go through the device. The RLHF tokenizer is literally the BPE tokenizer that we have been using throughout this exercise. So nothing needs to be explored here. So we'll take a quick peek. It is literally, if you pass a byte pair encoding directory, it loads the tokenizer, and we will reuse the tokenizer from the previous parts. So here is where we load, and then we have now the policy LLM. So if we go back to our definition, this is going to be our policy LLM that will start from the SFT frozen weights, and then we'll keep updating it. So if I take a look at it, it literally has two components: the actual LLM that we have seen before, and then there's a value head that will measure the estimated future rewards given a state and action for that generation. So at every token generated, we will have an estimate for the value and the logits coming in from the LLM. So once we again see this in action, things will be clearer. So this is my policy, and I load the state dictionary from the SFT frozen weights. I do this exact same with my reference. This will have frozen weights. So I'm immediately setting requires grad false and putting it in eval mode. This will never change throughout the exercise. This is just a baseline for me to compare how much I deviated from the SFT frozen weights. Then I'll run till this line to avoid the for loop. So I put it on eval mode, then I proceed. So in this block, I'm loading my reward model, and this is coming in from the checkpoint of part 7. So this, if you remember, is an encoder only model. that gives a scalar given a prompt and a response pair of what it thinks should be scored by the human. The optimizer. And then here, it's an all too familiar sampling of prompts that we're doing, this time from the alpaca dataset. This is the same dataset that we had used for our supervised fine-tuning, where we have the instruction and the input, we concatenate them together, and there is a response associated with it. So we only need to sample 16 prompts from here in order to do a mini batch training. So we'll proceed. All right, so we've gotten our prompts. Let's take a quick peek at it. Now, what I've done is I've only plucked out the corresponding prompts so that I can run the generation against these. So I don't have the answers with me right now over here. So I've got the different questions, which are the different combinations of instructions and the input for a particular batch. Now, in this case, I've set a batch size for 4, and we'll track it throughout the exercise. So I step into my training loop immediately. Feels weird to again go through a bunch of terms and directly jump onto the training loop, but I will unpack each and every one of these terms in context as I go along. So I've got my batch prompts over here. I'm checking for the length, and if it is less than the batch size, then I'm immediately just multiplying the number of prompts that I have. So in this case, I do have 4 prompts, so it did not go into the if condition. Now I'm going for a format prompt only by removing, and after that I'm removing the EOS token. So this will be ready for generation. So if I look at texts now, it will be exactly my prompts, but this time they will be formatted with my SFT format. So I've got the instruction and I've got the placeholder for the response. And now I'll be running my LLM for the generation. So here I'm literally in a for loop for each of the input prompt that comes in. I'm doing a policy.generate and appending all of it together in one single batch. So I'll run it till here. And now we've got 4 pieces of generation. So let's actually check them out. So I'm here in my debug console, and out IDs contain all of the token IDs that contain the prompt along with their response that is generated by our policy LLM. So if I look at out IDs, the first one, or rather this will have 4 elements. Let's quickly confirm that because our batch size is 4. So this has 4 elements. Now if I pluck out the first element and look at it, I will see a list of tokens. And now using our tokenizer, I can actually decode it. And you will see that this contains the instruction and this time the filled out response. So if I do this for a couple more in the batch, then you'll see that what are the primary colors? 3 primary colors are red, blue, and yellow. Now, these are the generations that we have seen before in our SFT stage. So they're aligned as per that. So we do a first cut model prediction here. Now, in the next stage, I will be generating my reward for each of these generations. So let's go ahead and explore that. Now, in my batch prompts, I've got my prompt. And now in my out IDs, I've got the prompt plus the LLM response. So I'm going to separate them out by creating a boundary. So given the prompt, I know how many tokens constituted my prompt. And if I subtract that from the out IDs, I will get how many response tokens I got, and then just decode those response tokens and then compute the reward given the prompt and the response text separated. So let me quickly run these couple of lines. So this full contains the entire response. And then from there, the prompt IDs contain just the prompt. And the boundary is the length of the prompt IDs. So if I go from boundary onwards and slice the full array, I will get my corresponding response IDs. And if I decode just that, I will get my response text. So if I were to look at it, you will see that response text only contains the answer to our query. So in goes the prompt and the response text. and out comes a reward scalar. So let's actually go inside this particular function, compute reward, and see what happens. So in this case, I'm dynamically importing the part 6 formatters and then formatting my prompt and response so that it again adheres to the instruction fine-tuned or the SFT format. So the prompt here is the raw prompt, and the response text here is the actual response that came in. So I'll have to format them again in the form of here. So they will have again the instructions and the response hashtag along with the VOS and EOS tokens respectively. So now I go and encode them, and with this encoded pair of prompt and response formatted, I can actually forward propagate through my reward model. So this reward model, if we've seen this before, let's quickly get into it and then check. So in comes a particular sequence of tokens. So the batch size is 1 because we're doing this one at a time. We have 99 such tokens. So we have the position embedding here. It calculates the age, the pad tokens, if any, and then it goes through the masked mean pooling that we have covered in the previous part. And then finally, the R head comes out, where R is going to be a scalar, and this is a reward for this particular prompt and response. So we'll come back, and we have computed the reward, and we are going to plug this out from the tensor and return it as a float. So if we see R scalar now, it'll just be a floating point number that represents the reward. Now in my data list, I'm appending the full set of tokens or token IDs, the boundary so that I know from where to split my full response, and the reward associated with it. So if I run this whole loop for the batch of 4 that I have, I will look at data, and then I will see that they are a tuple of 3 elements. The first element is the entire prompt plus response token IDs. The second element is the boundary beyond which the response tokens lie. And the third element is the reward. So I've got them organized like so. And then we move. Now in this section, we'll be doing a lot of list slicing gymnastics in order to make sure we honor the context length. Let me try and explain that with an example. So let's say we have a 256 context window. So this is going to be our context window. Now let's say I've got 250 tokens as the prompt, and then the response has 10 tokens. Now, if I'm going to put them together, then I'm actually going to get 260 tokens, which is exceeding my context length. So what I need to do now is I need to actually drop 4 tokens and then readjust my boundary. So the boundary here would have been 250, and then the tail end of the 10 tokens would have been my response set of tokens. But since this is exceeding my context window, I will actually have to clip this so that I'm only left with 240 prompt tokens, and I have all of my 10 response tokens. My apologies. So I have all my 246 prompt tokens, and I have my 10 response tokens. Put them together, I still honor my context window. So the idea is that you don't want to snip the response tokens by any stretch of the imagination. Those extra tokens that need to be evicted will go away from the prompt tokens. So if I quickly go through this, the policy context here is actually 256. So you see, this is 256. And then from there, I'm taking the minimum of the number of elements that are there in this particular batch's first token, and then the policy context. So this is the max length that I'm going to see in this particular batch. So my max length is going to be 159. So the idea over here is, in this batch of 4 sequences, 159 is the highest sequence that was seen. If anything beyond that, the way we saw in our example of the 260 tokens, it will be clipped to 256 tokens only. We've got our batch, we've got our sequence, mask, last index, and rewards initialization. We'll look at how these get filled up in a minute. So first things first, for the first prompt going in, I've got all of my tokens over here. So this will constitute the prompt and the response. So in our example that we saw, this can potentially be beyond 256, can touch 260, 270, whatever. Now here, we are taking the L-full and the max length. Now I know for a fact that the max length that I saw in this batch was 159. So this will always be a minimum of the number of tokens that I'm seeing in this particular example and the max length. So L in this case will be 99 only. Now from there, I do not need to drop any tokens because L full is 99 and L is 99. So drop becomes 0. And I'm going to take the max of, again, 0 and 0. So I'll be left with a 0. So this essentially depicts that since the prompt and the response combination is already part of my 256 context window, I do not need to evict any tokens. If this were the case that it exceeded the context window, then the drop will be more than 0 and we would have to evict tokens eventually. So the sequence is the actual sequence that was generated by the model, and that also includes the prompt. So again, if I look at the sequence, it's a bunch of zeros right now since it was initialized like so. And since we are going through the first loop, the first element of the sequence vector or sequence matrix will be filled up. So this will be filled up by everything that I've seen so far, including the response, which ends at the EOS token. And then from there, everything else will be padded to 2. So this is my pad token and everything else is padded to 2. So if I take a look at my sequence matrix once again, I will see that everything has been padded to 2. So from there, I'm creating a mask where the modified boundary, if my context window was exceeded, or if not, this B still acts as a generic term for the boundary. So from here, everything that was supposed to be part of the response becomes true. And then everything that was not supposed to be part of the response becomes false. So the response becomes true. Now everything to the left of it was the incoming prompt, which I don't want to track when I'm measuring rewards or when I'm measuring values or any other metric that I'll measure it against the generated tokens in the LLM and not the incoming tokens that were fed as prompt to the LLM. So everything to the right of the response will be the padded tokens, which also will be turned off. So again, if I look at the first element of mask, then all of these trues are the response token of the first sequence in my batch. That's what it means. So everything to the right are padded tokens. Everything to the left are prompt tokens. And then we move like so for the rest of the batch. And then if we relook at everything else, so we'll clear the console. And then now if I relook at my sequence, everything will be filled up. So this will include the prompt and the response, and then a bunch of padded tokens. And you will see that the last example in this batch had 159 tokens, so it does not have a pad token. And then from there, if you look at the mask, then everything that is true here was part of the response tokens, and everything that is false on the left was the prompt. Everything that is false on the right are the padded tokens. So this is the way it's structured. And now I will use all of this to eventually do further processing. I will now need to calculate my log probabilities. So for doing that, I need the policy model and the sequence of tokens. So let's go inside and check this out. Now, why do we need log probabilities? Now, if you look at the definition we've penned down before, the KL divergence measures the divergence between two probability distributions. Now, what we will do eventually is we'll keep updating the policy model and we'll freeze the reference model, and then we'll need to measure the difference or the divergence between the policy and the reference model in order to gauge how much deviation we're going through, so that we can either clip it or we can keep track of how much we are diverging from the SFT weights. Now, in order to do that, a way to calculate this is to simply have the ratio of the log of probabilities. So you have the log probs of the policy model and you have the log probs of the reference model, and then you simply take a ratio. Now we know for a fact that log has a very interesting property. So log P by log Q is simply log P minus log Q, and we are going to leverage this property as we go along. So we go inside calculating our log probabilities, and there's some gymnastics to kind of working this out as well. I really want you to follow this carefully. If required, freeze the video. If required, rewind and play back. It's essential that you understand this. It's not exactly a difficult concept, but it's just that it goes a lot of back and forth with the tokens and the positions, so it might be a little involved. So I get my input sequence. So in this case, if I check out x.shape, I get my batch of 159 tokens with the prompt and the response and the padded tokens all filled up. Now I'm going to forward propagate through my language model. So again, if you remember, the model is actually a policy with value model, which has the LM part, which is the large language model, and the value head, right? So we'll come back to this. So I'm going to forward propagate this, and what happens here? So the logits will be, again, as the LLM goes, if I am passing 159 tokens, for each of these 159 positions, I'm going to get 159 elements back, and each element will have a vocab size of 8,000 elements, which will signify the logit for each token in our vocabulary. So I'm expecting the shape of this logits to be 4 cross 159 cross 8,000. So let us quickly confirm this. So we're good here. So a batch of 4, 159 tokens each, and 8,000 potential token logits at each position. Now, in order to calculate the log probabilities, I will need labels associated with it. And as usual, we have been doing semi-supervised learning by treating the next token as our labels itself. So we're going to shift our labels to the right. Now, if you look at the implementation of shift labels, it's literally starting from the second element to the rest of the element. So my labels will start from the second token all the way till the end. So if I have 159 tokens going in, the labels will fetch me 158 tokens. So those are the right shifted tokens. So if I propagate this, then my labels will be 4 cross 158. Now, where did this 8,000 go? If you look at this carefully, we plucked out all of the elements till the last element. So let me sort of try and explain this with an example. So let's say I have a sequence of token 1, token 2, and token 3. Let's add one more. So this is the logits. Now, for the labels part, I'm going to right shift everything. So here I'll have T2, T3, and T4. That's it, right? So it has 3 elements only, because I took labels was the logits starting from the second element. And then the reason why here I have 8,000 candidates, here I have 8,000, and here I only have 1 is because if we come back and see this, then I'm actually doing a gather log probs, which does a log p dot gather. So we've got the documentation of torch.gather here. It takes in an input, the dimensionality and the index, and it will actually act upon the index on that dimensionality for that tensor. So I've got a tensor here just as an example. So I've got 1, 2, 3, 4. It's a matrix. And then I want to act along dimension 1. And then I want to provide these indices. So 0, 0 for the first one will ensure that the output becomes 1, 1. And then 1, 0 for the second position becomes reverse 4, 3. So this is how we can use gather to actually reshape a tensor as per how we want it. Now let's check out how we are going to use this in our use case. So I'll try and pull it up and show you with an actual example. So if I take this one, for example, and take the shape, now this will be 4 cross 158 cross 8000. So while the logit shape was 4 cross 159 cross 8000, this will be 4 cross 158 cross 8000. Since we are letting go of the last element, as we've already seen before, that's not relevant to the generation when you right shift your labels. So we've got 4 cross 158 cross 8000 over here that goes in to the gather. Now this logits are then undergo a log softmax. So this literally gives me the log probabilities. So if I were to get inside this function, I'm literally getting my log probabilities over here. So this log p will also be a 4 cross 158 cross 8000, but the values will be different. So if I were to look at the previous ones, these are raw logits. And if I were to look at log p, these will be the log probabilities, and you'll see that they're different in value, right? So this is the log of the probabilities. So we first apply a softmax, then apply a logarithm, and Torch has a function that does it in one step. So we go do that. Now this log p, I'm interested in getting the log probability of a particular position as per my label. So let me try and explain that. So if I were to look at my log p, or rather the shape of my log p, this has a batch size of 4, 158 tokens each, and 8000 vocabulary. Now let us grab the first batch. So if I grab the first sequence rather, then I have 158 tokens with 8000 candidates at each position. Now let us grab the first element from there. So I will have the 8000 candidates on the first positions. Now the log probability that I want to pick up. So if you see this, there are 8000 elements or 8000 candidate log probabilities. I need to pick one. So for each token position, I need to pick up one value for the log probability. And that value will be provided by the token ID of the label or of the right shifted label. So now if I go look at my label, it is 4 cross 158. Now if I pluck out the first sequence, then it will be 158 tokens. Now at each token, each value will represent the right shifted token ID. Now at this position 203, there will be a log probability present in our log p tensor, right? So now if I go look at the log p, pluck out the first sequence, pluck out the first token, and then pluck out the 203rd position of the log probabilities inside those 8,000, then I will get this value. Now, this is the value that I want to treat as my log probability for that token position. So this is, again, you can keep rewinding it. When I read it initially, it was a little confusing to me. Took a little time to wrap this in my head. So feel free to pause and rewind to really nail this. So I'll repeat what I said. So the position that the label contains is the log probability position you want to pluck out of your set of log P's. So log P, we take, and we can go through another sequence. Let's say we pluck out the second sequence, and then from there we pluck out the fifth token, and we have 8,000 candidates over here. Now, what I'm going to do is that I'm going to look at labels for the second sequence and for the fifth position. Now this says 297. So my log P over here will simply become the 297th position out of my 8,000 candidates. So for this, it will become minus 25.1141. So let's actually run this gather, and then let's confirm for this example that we have seen so far. So I've got my log P over here. So if I look at the shape of log P, it will be 4 cross 158. Now, if I take my LP for the first sequence and for the first position, I will see that it is minus 48.3569, which is exactly what we had seen when we had hand calculated the log P to align with my labels. So this is, and let us confirm this for the second one. So let's do it for the second sequence and the fifth position. And you will see that the value over here is minus 25.1141, which is exactly how we had hand calculated this. So this is how I'm going to calculate my log probabilities. I'm going to take my prompt and response input tensor. I'm going to encode it. I'm going to get the logits, calculate the loft softmax, get my labels through right shifting, and then use the gather function to use the label positions to pluck out the relevant log probability values at that particular token. So from there, I've got my log probabilities of my policy. And for all intents and purposes, this is the first training step that is running. And since our policy and reference starting point is literally the same set of weights, for the first iteration, this will exactly be the same, and the deviation will happen in subsequent steps as we optimize. So we've got our policy log probabilities and our reference log probabilities. Now the next thing, and we are all set for calculating the KL divergence, by the way. So this is good news. So if I were to revise all of what we have seen, we took all of our prompts, made that into a batch, did a lot of list slicing gymnastics to make sure we don't exceed the context window. And then from there, we've calculated the log probabilities. And now we are interested in calculating the values. So again, a quick refresher. The values is a simple linear head that spits out a scalar that represents the potential future reward that I will get given I'm following this policy for the foreseeable future till I hit the end state. So I'll come back here, and this time I'll run my sequence again through my policy, and I'm only interested in looking at the values. So now if I take a look at my values, I will get 159 values, and of course my batch size is 4. So this will have 4 cross 159. The value will be at a token level. So at each token, we assign a value that what is the estimate of the future rewards, what is the estimate of the cumulative future rewards at that particular position in that token. So once we do this, we'll have to align it with our shape of our log probabilities. So since we right shifted our labels, we've got only 158 positions there. So all I need to do is take all of the values and then ignore the end. So I'll do that, and my values becomes 4 cross 158. So let's go from there. Now, here I'm calculating a bunch of stuff. Let us go through it. Now, when you say, I want to measure the difference between log probabilities to calculate KL divergence, when you say that I want to calculate my values, I do not want to do it for the entire sequence. I'm only interested in doing it for the response tokens. So I don't want to do everything to the left of it, which is the prompt, and everything to the right of it, which is the padded tokens, because the value or the reward or everything that we are measuring will be against the generation or the response from the LLM. The prompt was already provided as an input, so there's no point of measuring anything there, right? So we are creating a mask where every response token will be true and everything else will be false. Now, if you look at it, we've created this mask here before. So if I were to relook at it, for every sequence, all the response tokens are true, everything else is false. And now I need to align my mask tokens against the 158 shape instead of 159. So again, if you check, it's 4 cross 159. I need to align it with this so that I can only measure the actions that I can measure my log probabilities against. So once I execute this, the action mask actually becomes 4 cross 158. Now, something interesting happens over here. So I'm going to take my policy log probabilities, and mind you, these are going to be 4 cross 158. So at each token position, I have a log probability assigned to it. Now, when I apply this action mask, this is a Boolean matrix. So when a Boolean matrix is applied to a matrix that has floats, what it does is it plucks out all of the positions where the action mask is true and ignores all of the rest. So if we look at our action mask, there are some trues, there are some false. Now let's actually measure the sum, and we've got 67 prompt responses on the first sequence, 19 response tokens on the second, 111 response tokens on the third, and 128 response tokens at the end of the sequence. And this is our batch. Now, if I take the sum of this entire batch, I have a total of 325 response tokens. So this entire batch has 325 response tokens, and I'm only interested in analyzing the log probabilities for these 325 response tokens. Everything else can be ignored. So I'm filtering my log probabilities for the policy and reference, and let me run them. So the old LP will become, will become 325 elements, and so will the reference log probability. And these, since we are running this for the first time, will be exactly the same. So if you check, minus 2.0981, minus 2.0548. Now this compared to the reference will be exactly the same, as we haven't done any updates to our policy yet. So these will be the exact same for the first time. Now, I'm also doing the same thing to my values. Again, I'm only interested in those 325 response tokens for the entire batch. So here are my values. So this will be the old values.shape, which will be 325. All right. So now, just like we saw the log trick where a ratio of logs can be taken as the difference, since we have the log probabilities already, we can measure the approximate KL as the difference in the logarithms. So we do that. And here is what we got. So we will get KL as 325 elements. All of them are 0 right now because we haven't made an update step yet, and literally the log probabilities of the policy model and the reference model are the same now. We now look at the rewards. So we take all of our rewards, which is again 4 cross 159. So we will have to take the second element onwards. And if you notice, we only receive a reward towards the end of our generation sequence. So if I look at this rewards, all of it taken from the first element onwards, you will see a ton of zeros. Now for this first sequence, I've got a reward here, which denotes the end of sequence for that, for this element. And then from there, I will have an end of sequence here, here, and here. So we've got a position here, we've got a position here, and I'm unable to find the one for the second one. And we've got a position here. There we go. So we only have one value for the reward at the position or where my generation ended at each sequence. So I'm taking that and again applying my action mask on top of it. So I'm only interested again in those 325 elements. So now I have a 325 elements, and I will have all of my rewards, all of my 4 rewards as part of these 325 elements. And then from there, I'm actually subtracting the KL divergence with the help of a coefficient as well. And this keeps me in check so that I don't drift far apart from my reference model. So the policy model and the reference model, their difference in log probability is the amount of divergence that they're going through. I'm penalizing my rewards for deviating too much. So this eventually, when we incorporate as part of the loss and then we backpropagate, this will ensure that, again, there's stability in the training, and there's we are trying to avoid catastrophic forgetting. So the shaped R literally becomes my returns. If we go back to our definition, then the returns is the discounted sum of future rewards for the rest of the generation. So we can see here that we have all of the rewards for that particular batch. So, and then we kind of subtract a penalty term using the KL divergence. And then the shaped R literally becomes the discounted rate, or the discounted set of rewards for the entire batch. So this will have again 325 elements where the rewards will be discounted by the KL divergence. Now in this case, the KL divergence is 0, so nothing got subtracted. So all of my reward terms are as is. All of my 4 reward terms in my batch are as is. So I've got an element here, 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 and here. So I've got 4 positions, rest of them is 0. Now, if I go back to my definition of advantage, it is how much better that token is than the model's average continuation in this context, which is measured by the returns minus the old values, the Q minus the V. Now, the value was the estimation or the estimation of my cumulative future rewards, whereas the returns are the actual rewards that I've gathered. So their difference will give me the advantage. Now, I'm also normalizing advantage here, again for stability. So we'll subtract the mean and divide it by the standard deviation. And I've just kept this term so that we can avoid zero division error. So we have our advantage. Now, if you take a quick look, then we know what the state is. It's the prompt. The action is generation of the new token. The policy is the LLM. The reference will be the frozen set that will always remain constant. We will never update that. The value of a state is the future rewards that we are calculating, and we are estimating this through a linear head in our LLM. So we added another linear head in order to measure the values. And again, we will have a value loss, and this will backpropagate, and our values estimation will get better over time. That's the expectation. The reward is literally coming from the reward model. The returns we've already seen is the actual hard rewards that you receive at the end of a batch generation sequence. We continue measuring our advantage. We now know what a KL divergence is, and we've also seen how to measure it by using the log probabilities. So a lot of terms were thrown at you in the beginning of the video. Hopefully now it's all unpacking and coming together. And then once we look at the PPO loss, everything will come together in one seamless way. So we've calculated our returns, we've calculated our advantage and normalized it. Now we are going to try and look at the update step. So this is where the actual policy weights are updated, and this is one training loop. Now, in a typical PPO or in a standard PPO, this highlighted block of code actually runs for multiple iterations for the same batch. So literally just think running a for loop over it so that this happens multiple times. Now, for simplicity's sake, we are only doing a single pass, right? So we set our policy model to train, and then again, if you go through multiple iterations of these in a for loop, so if you just do this block multiple times, then the policy will be different for every iteration in the loop. But for the first time, the logits new will be exactly equal to the logits that we have calculated previously. The values new will be exactly equal to the values that we've calculated previously. Again, keep in mind that here is where the actual policy weights update happens. So everything before that will be exactly the same. So think of this running in a for loop, and in the first iteration, this won't matter. This will just be equal to the previous logits that we have seen. So we grab the logits, we do a softmax, we grab the labels, and then we do a log p full.gather. This is the exact same operation that we do when we had tried to calculate our log probs. So we're doing a gather and then plucking out the log probabilities of the position specified in the label matrix, right? Then we apply our action mask, and then we get our new set of 325 values. So in this case, again, since this is only a single pass, everything here will be the same as the previous one, but eventually you should learn this or eventually run this in a loop of 4 or 8 iterations so that this goes through incremental updates on its own, right? So we finally come to the PPO losses, the calculation of the PPO losses, where we pass the new log P, the old log P, the advantage, the new values, the old values, the returns, and then we've got a couple of coefficients here that we'll watch once we enter this. So again, everything that we have run so far, I hope it all makes sense. So let's go inside how the PPO losses are calculated. So first things first, we take the new log P minus the old log P and the exponent of it, right? So again, when we run this in a loop, the new log P will be different than the old log P. Since we are doing a single forward pass or a single pass over our PPO, these will be exactly the same. So this will be a 0. Anything to the power of 0 is 1. So the ratio will be 1. So if you check, there we go. So the ratio is a tensor of ones, which has again 325 elements. Now, I next calculate my ratio times the advantage, unclipped, and then I'm actually clamping them. So if we look at torch.clamp, then we provide the input, the minimum, and the maximum, under which everything will be clipped. So we see here that the clip ratio is actually 0.2. So this ratio should be clipped between 0.8 and 1.2. So again, since the ratio here is pretty much 1, so we've got a 325 ones over here. So nothing gets clipped. The clipped and the unclipped are pretty much the same. We take the minimum of these and then we do a mean, and we store the negative of that as the policy loss. Again, for the first pass, this will be just the ratio times the advantage, and nothing will get changed. So if you look at the policy loss, you will see that it's a single tensor, right? Since we've gotten the mean. So this will be our policy loss. And then from there, the values that I tried to estimate that would have been my cumulative sum of the future rewards and the returns that I actually got should be very close to each other. So I'm measuring the MSE loss here and calling it the value loss. So we go through it, the value loss. Now the entropy is another interesting element over here. Now the entropy specifies, or rather it's a term that penalizes a lot of confidence or a lot of deterministic behavior. Let me try and explain this with an example. So I'm taking the log p and taking the mean of it. So if my LLM is hyper confident, all of my probabilities will be 1. So let's say we're doing a 3 token generation and all of my probabilities will be 1. What is the log of 1? It's a 0. So the entropy here will become 0, which essentially means nothing will get added to the final loss. So I'm calculating the total loss over here and adding the entropy to it. And if my model is hyper confident, nothing will be added. But if my model is diffusing tokens well, let's say for 3 token generation, it has these confidences each respectively. Mind that they don't have to sum up to 1, of course. So I can make them a little random. And if I take the log of this, for example, so if I take the ln of 43, then I get a minus 0.84. Now, when you get a minus 0.84 and put a minus sign there, it becomes a plus 0.84. So a positive term gets subtracted from the loss. So I'll repeat this. If your probabilities or your confidences are lower, then the entropy is higher and it's a positive number, which then gets subtracted from the loss. So what the entropy is trying to do is promoting exploration. So in reinforcement learning, the two things that you need to balance out is exploration and exploitation. If you become too deterministic, you might get stuck at a local minima, and that goes for more exploitation than exploration. The entropy term is trying to balance that out. So we are not using the entropy term here. We are zeroing it out, but it's a fun exercise to set it some value and see how it goes. So from there, I take my difference of the logs, the log probabilities, and take the mean to get my final KL divergence. So this will be one particular term, which will be the mean. So again, since my old and new are literally the same policies, this time I'll get 0. But if you run it in a loop, as a standard PPO does, you will get different values from the second iteration onwards. So my total loss is the policy loss plus the value loss, and then I'm able to control it with a hyperparameter, the VF coefficient, and the entropy. I'm again able to control it with an entropy coefficient. That constitutes my total loss, which then is outputted with the help of a data class that I have defined over here. So we have the policy loss, value loss, entropy, approx KL, and of course, the amalgamation of all of these terms into a final total loss. So we go from there. This becomes our total loss, and then we backpropagate. And then from here, now my policy model has undergone a backpropagation, so its weights have changed. So the policy model has literally now become a new large language model that is different from the reference model that we had frozen in the previous step. So I will be in a position to measure the log probabilities now for the policy and actually compare them with the reference. And then at every 10 steps, I'm actually printing out the different metrics that I've measured with the overall loss, and this should hopefully suffice in our training workflow. So without further ado, what we will do is stop this entire sequence and then go straight for the training. So in our orchestrator, we've got a training run over here with the batch size 4 and all of the hyperparameters set in. I've got the reward model checkpoint, the SFT checkpoint, and then now we train. So we're training for 50 steps and we'll log every 10 steps. And you will see that based on the metrics, we started with a loss that seems to be eventually going down, trending down. I've got the value loss, which again gets better at estimating the future discounted rewards. The movement of KL from one step to the other. So this is at a per step level. So whatever I had as a policy at step 1 versus what I have as a policy now. So this is the temporal movement of the policy model. And then from there, I have the KL divergence measured between the policy and the frozen reference model. So you will eventually see by training this for a lot of steps that this grows over time. So it starts with a tiny number and then it eventually grows over time, right? So finally, we have the eval to look at. Now, this will be, again, fairly simple. So let us quickly check this out. So all we need to pass here is the policy checkpoint, the reward checkpoint, the split, and the BP directory. And just to compare it against what we had in the reference, I will also load the SFT model or the reference model so that we can compare how the generation has changed. Now, obviously, the reward model that we have is not the best reward model, and calibrating to that will actually worsen the responses. But the whole idea is to show you that the policy model and the reference model deviation. So without further ado, let's put this in debug mode. Let's actually turn our training off. We've done it already. And then in the eval step, we have this. So we load our tokenizer, we load our policy that we have trained in this step. So we load that, and then we load the reference model that is coming from the SFT part. And this we are only doing so that we can compare, right? So we go through, we need our reward model. So there we go. And for sample prompts, let's actually go through one prompt and see what is going on. So P is a particular prompt that we are interested in measuring against, and just to check out what is going on. So give 3 tips for staying healthy. All right. So we have the prefix, the IDs, we do the X, and then we do policy.generate, reference.generate. And then we get the response decoded and the response old. So if I look at the response old, I will see that this will be the exact same output of my SFT model. And this also incidentally seems to be the exact same. So what we'll do is we'll try and train it for more steps and see if that changes. So I've got actually this run over here, which will train for, I think, 100 steps. And then let's check it out. So I've disabled all the breakpoints in the training. We'll only look at the eval step. So we run our tests as usual, and then we start the training, this time for 100 steps. And then from there, we can see our losses moving, the different losses. So we've got the overall loss, the value loss, the KL movement, the temporal movement of the policy, and the overall KL divergence from the model. So we've hit our eval, and we'll just go through the area till where we generate our responses. So we've got all of that till here, and hopefully things will be different in this run. So I've got the response over here, which now devolves to something else, since we have trained our policy as per the RLHF framework. But if we look at the old model, it will still be the same. So we have significant deviation from where we started. So this essentially is what reinforcement learning from human feedback constitutes. You've got the reward model on one side, and then we do proximal policy optimization to align it to human preferences by using the reward model to represent as a proxy for the human preference score. So obviously, again, for a 2-layer neural network for 16 data points, this all won't make a lot of sense. You actually need a lot of data. So if I again come back to this, then the reinforcement learning part, it's a pretty tricky model to optimize. So you've got the policy, the reference, and a lot of stability tricks that we have used in terms of computing the advantage and normalizing it, in terms of using the KL coefficient to kind of penalize the reward. So all of it put together, hopefully this all now comes together in your head. I recommend watching this video twice, thrice over multiple days. Maybe do a bunch of forward passes over this video to really consolidate this in your head, and then back that up with a lot of theoretical understanding of the different concepts that we've gone through. And I'm sure everything will come together beautifully to make sense, right? So in this part, we've done policy network, the reward signal, the PPO objective, the training loop, and some of the stability tricks. So I hope you had a lot of fun going through this series. I did, at least, and it kind of sort of cleared a lot of concepts that were unclear to me, especially when you come down to implementation. So I highly recommend you grab your laptops and coffee and code along with this entire series, and hopefully you have your own takeaways from this as well. Thanks a lot for your time.